3 times every day, something on the edge of the universe explodes with so much force that it outshines 1 trillion suns. And for a few seconds, maybe a few minutes, that explosion floods across billions of light-years of empty space, washing over planets and moons and solar systems that will never know it happened, unless it happens close enough. Then everything ends, not gradually, not with warning, just ends. These are gamma-ray bursts, the most violent events in the known cosmos, and orbiting satellites have been quietly logging them for decades, one after another, flashing across our sky while you sleep, while you work, while you scroll past this video, deciding whether it's worth your time. Most people have no idea they exist. Fewer still understand what they actually are. And almost no one has seriously considered what happens if the next one occurs inside our galactic neighborhood instead of safely across the void. But gamma-ray bursts are just the opening act. Because the universe is not the cold, indifferent, mostly empty place we like to imagine when we look up at the stars. It is alive with forces we barely understand and phenomena that defy every model we've built to explain them. Black holes that swallow star systems whole. Rogue planets hurtling through the dark with no sun to anchor them. Stellar explosions 10 times more violent than anything we thought physics allowed. And underneath it all, woven into the very fabric of space itself, invisible forces we have named but cannot see, cannot touch, and cannot explain. This is not a video about distant abstract threats that will never matter. This is about what is actually out there right now, what we've found, what we've measured, and what we still cannot explain. The void above us is not empty, and we are not safe. Welcome to Magnetic Space. If you're new here, please subscribe. We make these documentaries every day, and honestly, we'd love to have you along for the ride. Before we begin, tell us in the comments where you're watching from and what time it is there. Now, settle in. This is going to be a good one. 3 times a day, while you're checking your phone, driving to work, or arguing about what to watch on television, a flash of light erupts somewhere in the universe, bright enough to outshine every star in an entire galaxy combined. And for a few seconds, sometimes a few minutes, that flash becomes the brightest thing in the observable cosmos, brighter than 1 trillion suns, brighter than anything else that exists except the echo of the Big Bang itself. The light travels across billions of years of space, carries more energy than our sun will produce in its entire 10 billion year lifetime, and by the time it reaches Earth, it's invisible to your eyes. You will never see it, you will never feel it. And unless you happen to work at one of the handful of space agencies monitoring gamma-ray detectors in orbit, you will never know it happened. But it did happen. It's happening right now. And it will happen again in about 8 hours, whether you're paying attention or not. The phenomenon has a name. Astronomers call them gamma-ray bursts, and they are the most violent explosions in the known universe. Not the biggest in terms of volume, not the longest lasting, but the most concentrated release of pure electromagnetic energy physics allows outside of the moment creation itself began. They are so powerful that a single burst, if it occurred close enough and happened to be aimed in our direction, could strip the ozone layer off this planet, flood the surface with radiation, and trigger a mass extinction event faster than you could pack a suitcase. And we detect roughly 1 per day. The video title says 3, and depending on how you count, that's not wrong. Some days we catch 3. Some days we catch none. On average, satellites pick up about 1 confirmed gamma-ray burst every 24 hours, a number that has held steady since we started watching the sky with the right instruments in the late 1990s. If you're sitting there doing the math, that's 365 cosmic detonations per year, most of them happening billions of light-years away in galaxies whose names you will never hear, whose light takes longer to reach us than multicellular life has existed on Earth. The flashes are old, they are distant, and they are completely, fundamentally, disturbingly real. Here's what a gamma-ray burst actually is. Take a star, not a small one, a massive one, something between 5 and 10 times the mass of our Sun. Let it burn through its fuel the way massive stars do, fast and recklessly, fusing hydrogen into helium, helium into carbon, carbon into oxygen, oxygen into heavier elements, climbing the periodic table until the core is pure iron. Iron doesn't fuse. Iron is the end of the line. When the core runs out of fuel, there is nothing left to hold the star up against its own gravity. The core collapses. In less than a second, a ball of matter the size of a city gets crushed into a point so dense that it punches a hole in space-time and becomes a black hole. The outer layers of the star, which have been falling inward, slam into that newborn singularity and rebound outward in a supernova. Except in this case, something else happens. The collapsing core doesn't just form a black hole. It forms a black hole that's spinning, fast, and it drags the surrounding magnetic fields into a twisted knot of energy so intense that it fires 2 jets of particles outward along the rotational axis at 99.9% the speed of light. Those jets punch through the dying star, break into open space, and begin radiating gamma rays. That's a gamma-ray burst. A beam of focused death fired from the corpse of a star, narrow as a spotlight, bright as a cosmic flare gun, lasting anywhere from a few milliseconds to several minutes before the engine runs out of fuel and the light blinks off forever. There are 2 kinds, and the difference matters. Long gamma-ray bursts last more than 2 seconds. Sometimes they last minutes. These are the ones tied to massive star collapses, the ones where a black hole forms and a supernova follows, the ones that signal the violent end of something that used to shine. They make up about 70% of all detected bursts. Short gamma-ray bursts last less than 2 seconds, often less than 1. These come from a different kind of catastrophe. 2 neutron stars, each one a city-sized ball of matter so dense that a teaspoon of it would weigh 1 billion tons, spiral into each other after orbiting for millions or billions of years. When they merge, the collision releases a gravitational wave that ripples across the fabric of space-time itself. And in the final instant before they touch, the magnetic fields around them twist into the same kind of jet-launching configuration that happens in a collapsing star. A short gamma-ray burst erupts, violently, briefly, and then the merged object either becomes a black hole or a single heavier neutron star, depending on the mass. Either way, the result is the same. A flash of gamma radiation so intense that if you were standing on a planet a few hundred light-years away and that beam happened to swing past your sky, the atmosphere above you would ignite. How much energy are we actually talking about? The numbers are large enough that they stop meaning anything unless you anchor them to something familiar. A typical gamma-ray burst releases about 3 times 10 to the 44th joules of energy. For comparison, a supernova, the explosion of an entire star, releases about 10 to the 44th joules. A gamma-ray burst is 3 times that, and it does it in seconds. Our Sun will burn for roughly 10 billion years, fusing hydrogen into helium at a steady rate, producing light and heat and the occasional solar flare. Add up every joule of energy the Sun will ever produce over its entire lifetime, from the moment it ignited 4.5 billion years ago to the moment it will die 5 billion years from now, and you get a total energy budget of about 10 to the 44th joules. One gamma-ray burst in 30 seconds outputs more energy than our Sun will manage in 10 billion years. Some bursts go higher. One event recorded in the early 2000s released an estimated 300 times the Sun's total lifetime energy output in under a minute. That's not an exaggeration. That's the measurement. Scientists ran the numbers twice to make sure they hadn't misplaced a decimal point. They hadn't. For the brief duration of a gamma-ray burst, the explosion becomes the brightest source of electromagnetic radiation in the observable universe, brighter than all the other gamma-ray sources combined, brighter than the supernova that triggered it, brighter than the entire galaxy it's sitting in. If you were somehow able to build a gamma-ray telescope powerful enough to resolve individual objects across billions of light-years, and you pointed it at the sky during one of these events, the burst would blind the instrument. You would have to look away, which, in cosmic terms, is a sentence that should not be possible. There is nothing in everyday human experience that prepares you for an object so luminous that looking at it from across the universe is dangerous. We didn't discover gamma-ray bursts by looking for them. We stumbled into them by accident while trying to catch the Soviet Union cheating on a treaty. In the 1960s, the United States launched a series of satellites called Vela, designed to monitor the Earth and surrounding space for gamma-ray flashes that might indicate a nuclear weapon test. The Atmospheric Test Ban Treaty, signed in 1963, prohibited above-ground nuclear detonations, and the Vela satellites were the enforcement mechanism. If anyone set off a bomb in the atmosphere or in space, Vela would see it. And Vela did see flashes, lots of them. But they weren't coming from Earth, and they weren't coming from the Moon or anywhere near our solar system. They were coming from deep space, random directions, no pattern, no repeats. The military sat on the data for years, not sure what to make of it. In 1973, the findings were finally declassified and published in the Astrophysical Journal. Astronomers read the paper and realized they had just inherited a mystery nobody had asked for. Explosions from random directions in space, each one lasting seconds, each one releasing absurd amounts of gamma radiation, each one appearing exactly once and never repeating. The sources, whatever they were destroying themselves in the process of going off. It took another 2 decades to figure out how far away they were. Early theories assumed gamma-ray bursts were local, maybe flares from neutron stars in the Milky Way, or strange events happening within a few thousand light-years of Earth. Then, in 1991, NASA launched the Compton Gamma Ray Observatory, which carried an instrument called BATS, the Burst and Transient Source Experiment. BATS was designed to catch gamma-ray bursts and map where they came from. Over the next 9 years, it detected more than 2,700 of them, and when astronomers plotted the directions on a map of the sky, they found something unsettling. The bursts were distributed evenly in all directions, no clustering near the galactic plane, no concentration toward the center of the Milky Way, just a perfectly isotropic scatter, the kind of pattern you only get when the sources are either sitting right on top of you or sitting so far away that the shape of our galaxy stops mattering. Given the energy levels involved, the first option was ruled out immediately. These things were not nearby, they were cosmological. Billions of light years out, sitting in distant galaxies, releasing energies large enough to be seen across the entire observable universe. That realization changed everything. Once astronomers knew the distances, they could calculate the energies, and the energies were terrifying. It also meant that gamma-ray bursts, despite being the most powerful explosions in the universe, were not aimed at us. The beams are narrow, a few degrees wide at most, fired along the rotational axis of whatever object is producing them. If the beam isn't pointed at Earth, we don't see it. We only catch the bursts where the jet happens to sweep across our patch of sky. which statistically is a small fraction of the total number occurring. For every gamma-ray burst we detect, there are dozens, maybe hundreds, happening in orientations we'll never see. The universe is going off like a fireworks show, and we're only catching the ones aimed vaguely in our direction. In November 2004, NASA launched the SWIFT satellite, a dedicated gamma-ray burst hunter designed to catch bursts as they happen, and slew its telescope toward the source, fast enough to observe the afterglow in other wavelengths. By the time SWIFT was decommissioned, it had logged nearly 1,000 gamma-ray bursts, each one tagged with a position, a duration, and a brightness. In June 2008, the Fermi Gamma-Ray Space Telescope went up, carrying an instrument called the Gamma-Ray Burst Monitor. Fermi is still operating, and as of this writing, it has detected more than 1,700 bursts. Between SWIFT, Fermi, and a handful of other missions, the detection rate holds steady at roughly 1 burst per day. Some days we see 3, some days none. The average is 1, and that average has not changed in 20 years. The universe, it turns out, runs on a schedule. Not a precise one, not a predictable one, but a statistical one. Somewhere out there, every 24 hours, a massive star collapses or 2 neutron stars collide, and a beam of gamma radiation tears through the surrounding space at nearly the speed of light. If you happen to be floating in open space a few hundred light years from one of those events, directly in the path of the jet, you would not have time to register what was happening. The gamma rays would hit you at light speed. By the time the information that you were being irradiated reached your brain would already be ionized vapor. There would be no pain, there would be no flash of light. There would just be a moment where you existed, and then a moment where the atoms that used to be you no longer remembered how to hold a shape. That sounds like science fiction. It is not. In 2023, astronomers detected something that had never been seen before. A gamma-ray burst that repeated over the course of a single day. Not a faint echo, not a secondary flare. A full repeat from the same source outside our galaxy. Gamma-ray bursts are not supposed to do that. The whole point of a gamma-ray burst is that it's a one-time event. The star collapses once, the neutron stars merge once. The explosion happens, the source destroys itself, and that's the end of the story. This one didn't follow the script. It went off, paused, and went off again hours later from the exact same location. As of now, no one has a confident explanation for what happened. The data is still being analyzed. The models are still being revised. The event sits in the journals like a footnote that doesn't fit, and every astronomer who works on gamma-ray bursts is quietly aware that the rules they thought they understood might need an asterisk. There was another moment back in 2009 where a gamma-ray burst taught us something fundamental about the universe itself. A short burst was detected, and astronomers measured the arrival times of gamma-ray photons at different energies. Some photons carried 1,000,000 times more energy than others. According to some theories of quantum gravity, space-time at very small scales might be grainy, like pixels on a screen, and if that were true, high-energy photons would travel slightly slower than low-energy ones over cosmological distances. The difference would be tiny, but over 7 billion light-years it should add up. The photons from the 2009 burst arrived within 1 second of each other, despite differing by a factor of 1,000,000 in energy. Space-time, it turns out, is smooth. Einstein was right. Again, the gamma-ray burst didn't just explode. It ran an experiment on the structure of reality and gave us an answer we didn't know we needed. So here we are, sitting on a planet orbiting an average star in an average galaxy, while the universe fires off one of the most violent events physics allows roughly once per day. Most of them are too far away to matter. Most of them are aimed somewhere else, but not all of them. And that brings us to the question nobody wants to ask out loud, but everyone has thought about at least once after learning what a gamma-ray burst actually is. What happens if one goes off nearby, close enough to matter, aimed directly at Earth? What happens when the beam, instead of missing us by a comfortable margin of billions of light years, passes through this solar system and washes over the atmosphere at full strength? That scenario is not hypothetical, it is just unlikely. And the difference between those two words is the only reason you're still here to read this sentence. The question isn't whether a gamma-ray burst could destroy life on Earth. The question is how close it would need to be to actually do it. And the answer, depending on which astrophysicist you ask and which model they trust, sits somewhere between uncomfortably close and terrifyingly closer than you'd think. The kill zone for a gamma-ray burst aimed at our planet isn't measured in miles or kilometers. It's measured in light years, thousands of them, and the radius of danger is large enough that multiple candidates within our own galaxy could theoretically end us if the geometry lined up wrong and the universe decided today was the day. Let's start with the numbers, because the numbers are where the arguments begin. A gamma-ray burst occurring within 5,000 to 8,000 light-years of Earth and aimed directly at us would be what researchers politely call a lethal event. Lethal in this context does not mean a few people get sick. It means mass extinction, food chains collapse, ecosystems unravel. The kind of biological catastrophe that shows up in the fossil record as a boundary layer where everything below it is diverse and thriving and everything above it is noticeably less so. Some models push the danger zone closer, others stretch it farther out. A study from NASA and the University of Kansas calculated that a gamma-ray burst within roughly 6,500 light-years has about a 50% chance of having caused a lethal event sometime in the last 500 million years. 50% is not a comforting number when the thing you're talking about is planetary sterilization. It means the odds are essentially a coin flip that this has already happened to Earth at least once since complex multicellular life got started. For a gamma-ray burst to completely sterilize the surface, to kill everything down to the most radiation-resistant bacteria huddled in the deepest caves, the burst would need to occur much closer, within about 33 light-years according to some estimates. At that range, the direct cosmic ray dose reaching the ground would cook anything with DNA. The air itself would ionize. The surface would be bathed in radiation levels comparable to standing inside a nuclear reactor core with no shielding. Fortunately, the odds of a gamma-ray burst happening that close are vanishingly small. There are no candidates within 33 light-years capable of producing one. The nearest star, massive enough to collapse into a black hole and fire a gamma-ray burst, is much farther out. We can cross that particular nightmare off the list. The problem is that you don't need to sterilize the planet to cause a mass extinction. You just need to break the atmosphere. Here's what happens when a gamma-ray burst hits Earth from a few thousand light-years away. The beam itself, traveling at the speed of light, arrives without warning. There is no early detection system that would give us time to prepare. Gamma rays do not slow down. They do not announce themselves. One moment the sky is normal. The next moment the upper atmosphere is being hammered by a flood of high-energy photons, carrying more energy per particle than anything the sun produces on its worst day. Those photons slam into nitrogen and oxygen molecules in the stratosphere and ionosphere, ripping electrons off atoms, breaking chemical bonds, generating cascades of secondary particles. The air lights up. Not in a way you would see from the ground, not in visible wavelengths, but the instruments designed to monitor atmospheric chemistry would go haywire. Within seconds, the burst begins shredding the ozone layer. Ozone is a molecule made of 3 oxygen atoms, and it exists in a thin diffused shell roughly 15 to 30 kilometers above the surface. It doesn't sound like much. The entire ozone layer, if you could somehow compress it down to sea level pressure, would form a blanket about 3 millimeters thick around the planet. 3 millimeters. That's all that stands between the surface of the Earth and the full, unfiltered ultraviolet output of the Sun. Ozone absorbs ultraviolet B and ultraviolet C radiation, the wavelengths that directly damage DNA, proteins, and cell membranes. Without ozone, life on land becomes difficult. Without enough ozone, it becomes impossible. A nearby gamma-ray burst, lasting just 10 seconds, can destroy up to 50% of the ozone layer. 50% gone in 10 seconds, and it doesn't come back quickly. The chemistry that replenishes ozone operates on timescales of years. Current models suggest it would take at least 5 years for the ozone layer to recover after a nearby gamma-ray burst, and during those 5 years, the surface would be exposed to ultraviolet levels no complex organism on Earth evolved to survive. The destruction mechanism is indirect but efficient. Gamma rays hitting the upper atmosphere generate nitrogen oxides, molecules made of nitrogen and oxygen that wouldn't normally exist in large quantities at those altitudes. Nitrogen oxides are ozone killers. They catalyze the breakdown of ozone molecules in a chain reaction where a single nitrogen oxide molecule can destroy thousands of ozone molecules before it's finally removed from the atmosphere. The more gamma rays hit, the more nitrogen oxides form, and the faster the ozone layer disintegrates. The burst itself lasts seconds. The chemistry it triggers lasts years. By the time the gamma-ray flux drops back to zero and the sky returns to normal from a radiation perspective, the damage is already done. The ozone is gone, and now the sun, which has been shining the same way it always has, becomes a threat. Ultraviolet B radiation increases at the surface. How much depends on latitude, season, and how much ozone is left. But the models suggest DNA damage rates could climb to 16 times normal levels in the years following a nearby gamma-ray burst. 16 times, that's not a minor increase. That's the difference between a sunny day and standing under a sun lamp designed to sterilize laboratory equipment. Humans would notice. Skin cancer rates would skyrocket. Cataracts would become epidemic. Anyone spending significant time outdoors without heavy UV protection would be trading sunlight for sickness. But humans are adaptable. We could retreat indoors. We could wear protective clothing. We could, in theory, survive a few years of elevated UV by changing behavior. The problem is that most of the biosphere can't. Phytoplankton are the base of the ocean food chain. These are single-celled organisms, microscopic, floating near the surface where sunlight penetrates. They perform photosynthesis, convert carbon dioxide into oxygen, and serve as food for everything from krill to fish larvae to whales by way of a dozen intermediary steps. They are also extremely vulnerable to ultraviolet radiation. Their cells have nowhere to hide. They float in the top few meters of the ocean, fully exposed, and their DNA repair mechanisms are not built to handle 16 times normal UV for years on end. A significant die-off of phytoplankton crashes the marine food web. Fisheries collapse, coastal ecosystems unravel. The oxygen production rate drops. Phytoplankton are responsible for roughly half the oxygen in Earth's atmosphere. Kill enough of them, and the air starts to change, not overnight, but over decades, over centuries, in ways that feed back into every other system on the planet. On land, the situation is similarly grim. Plants handle UV better than phytoplankton, but only up to a point. Many crops, especially those we depend on for food, are UV sensitive. Wheat, rice, soybeans, all of them show reduced growth and lower yields when UV exposure climbs past certain thresholds. Wild plants fare no better. Forests thin, grasslands weaken. Insects, which are already facing population declines for unrelated reasons, take another hit because the plants they depend on are struggling, and because many insect species are directly UV sensitive themselves. Birds that eat insects face food shortages. Mammals that eat plants or insects or birds face food shortages. The whole pyramid starts to wobble, and at the bottom of it, holding everything up, is a broken ozone layer and a sun that hasn't changed its behavior at all. It's just that we've lost the shield. There's another effect, quieter but no less dangerous, that some models predict. They call it a gamma-ray burst winter, and the mechanism is ecosystem collapse. With phytoplankton dying off, the ocean absorbs less carbon dioxide. With plant growth suppressed on land, forests and grasslands absorb less carbon dioxide. The carbon cycle, which normally moves carbon between the atmosphere, oceans, and living things in a rough equilibrium, gets disrupted. At the same time, nitrogen oxides in the atmosphere, the same compounds destroying ozone, also affect atmospheric chemistry in ways that can alter cloud formation and aerosol distribution. Some researchers think the combined effects could trigger a period of global cooling, not from the burst itself, but from the cascading environmental changes that follow. Lower temperatures, disrupted weather patterns, collapsing food webs, all happening at once, all because a star collapsed 6,000 light-years away and happened to be aimed in our direction when it went off. And here's the part that should keep you awake. We have evidence this kind of thing has happened before. Not gamma-ray bursts specifically, we'll get to that, but nearby cosmic explosions that left marks on Earth. In ocean sediments, trapped inside fossilized bacteria that lived millions of years ago, scientists have found iron-60. Iron-60 is an isotope that does not occur naturally on Earth. It's produced in supernova explosions and scattered into space when massive stars die. The only way it ends up in Earth's ocean floor is if a supernova went off close enough for the debris to reach us. 2 events have been identified so far, one roughly 6.5 to 8.5 million years ago, another around 2 million years ago. Both events left detectable traces of iron-60 in sediment layers that correspond to those time periods, and both events indicate supernovae occurred within a few hundred light-years of Earth, not close enough to cause a mass extinction, not close enough to destroy the ozone layer, but close enough that we were touched by the aftermath. The debris drifted through the solar system. Some of it fell into the atmosphere, and some of it ended up in the ocean, where bacteria absorbed it and eventually fossilized, preserving the signature for researchers to find millions of years later. Supernovae are not gamma-ray bursts. A supernova is the explosion. A gamma-ray burst is the focused jet that sometimes, not always, accompanies the explosion if the geometry and spin and magnetic fields line up just right. The iron-60 findings tell us that nearby supernovae have happened within recorded geological time. They do not tell us whether those supernovae also produced gamma-ray bursts or whether the bursts were aimed at us. But they confirm something important. Earth sits in a neighborhood where massive stars occasionally die, and when they die, we feel the effects even from hundreds of light-years away. If one of those stars had been oriented differently, if the jet had been pointed at Earth instead of off into empty space, the iron 60 in those sediment layers would be the least interesting thing researchers found. They'd be looking at extinction boundaries. There is no definitive proof yet that a gamma-ray burst has caused a mass extinction on Earth. But the absence of proof is not proof of absence, and several researchers have pointed to extinction events in the fossil record that line up suspiciously well with what you'd expect from a nearby burst. NASA scientists and researchers from the University of Kansas published a study suggesting that a gamma-ray burst may have triggered a mass extinction hundreds of millions of years ago by stripping the ozone layer and exposing the surface to lethal ultraviolet levels. The event they point to is the Ordovician-Silurian extinction, one of the 5 largest mass extinctions in Earth's history, which occurred roughly 440 million years ago. Around 60% of marine species disappeared. The extinction happened in 2 pulses separated by hundreds of thousands of years, and the second pulse coincides with evidence of a sudden climate shift and changes in ocean chemistry. The pattern fits. Ozone destruction, UV spike, phytoplankton collapse, marine food webs unravel, extinction follows. The timing is right, the victims are right, the mechanism works. What's missing is a smoking gun, some isotopic signature or chemical marker that definitively points to a gamma-ray burst, rather than some other cause like volcanism or an ice age or an asteroid impact. The data is circumstantial, which means the argument remains open. But it also means we can't rule it out. Statistically, the odds that Earth has been hit by a lethal gamma-ray burst at some point in its history are uncomfortable. One study calculated that there is a very good chance, not certainty, but a very good chance, that at least one lethal gamma-ray burst occurred within the past 5 billion years, close enough to significantly damage life. 5 billion years is roughly the age of the Earth. That means, in the time our planet has existed, the odds are favorable that we've been on the receiving end of one of these events at least once, maybe more. The Milky Way produces an estimated 1 long-duration gamma-ray burst every 10,000 to 1 million years, depending on which models you trust. Most of those bursts are aimed away from us. Most occur far enough away that the beam dissipates before it reaches Earth. But over 5 billion years, you don't need many close calls to hit the bad luck threshold. You just need one poorly aimed jet from a collapsing star that happened to point at a blue-green planet in the middle of nowhere that, at the time, was minding its own business, evolving complex life. The nearest known gamma-ray burst candidate in the Milky Way is a star system called Wolf-Rayet 104. It's about 8,000 light-years away, a binary system where a massive Wolf-Rayet star is orbiting a companion star, both of them nearing the end of their lives. Wolf-Rayet stars are the kind of massive, fast-burning objects that can produce gamma-ray bursts when they collapse. Wolf-Rayet 104 is one of them. At 8,000 light-years, it sits right on the edge of the danger zone. If it goes off tomorrow, and if the jet happens to be aimed at Earth, we are looking at ozone depletion, UV exposure, ecosystem collapse, the whole scenario. We wouldn't know it was happening until the gamma rays arrived. No warning, no time to prepare. Just a sudden flood of high-energy radiation hitting the atmosphere, and by the time we detected it, the damage would already be underway. The good news, if you can call it that, is that the odds of the jet being aimed at us are low. Gamma-ray burst jets are narrow, only a few degrees wide. The universe is large. The chances that Wolf-Rayet 104 is oriented with its rotational axis pointing directly at Earth are slim. Slim is not zero, And 8,000 light-years is not comfortably far. It's just far enough that most people don't think about it. There are other candidates. Eta Carinae, a massive star system roughly 7,500 light-years away, is another one. It's unstable, prone to outbursts, and expected to go supernova sometime in the astronomically near future, which could mean tomorrow or could mean 1,000,000 years from now. If Eta Carinae produces a gamma-ray burst, and if the jet is aimed at us, the outcome is the same. Ozone destruction, UV flood, extinction risk. The list of nearby massive stars that could theoretically kill us is short but not empty, and every single one of them is a ticking clock with no visible numbers on the dial. The universe doesn't care about fair. It doesn't care about timing or readiness or whether we've figured out how to detect these events before they hit. A gamma-ray burst travels at light speed. By definition, we see it the moment it arrives, and the moment it arrives is the moment the atmosphere starts breaking apart. There is no evacuation plan. There is no shelter deep enough. If the burst is strong enough and close enough, the only thing standing between us and a planetary catastrophe is luck. The luck that the star collapses with its jet aimed somewhere else. The luck that the burst happens far enough away that the beam spreads and weakens before it reaches us. The luck that we happen to be living in a quiet period of galactic history where the nearby massive stars are stable and the ones that aren't are aimed in the wrong direction. For now, that luck is holding, but the galaxy is not empty and the stars that can kill us are still burning. Some of them are close, and at least one of them, somewhere out there, is probably minutes away from collapsing. You just don't know which one, and neither does anyone else. The sky above you right now looks calm, the stars are steady, the ozone layer is intact. But somewhere in the Milky Way, maybe within a few thousand light-years, maybe farther, maybe closer, a massive star is running out of time. Its core is filling with iron. The fusion reactions that have held it up for millions of years are sputtering. And when the core finally collapses, if the jet points this way, the sky will stop being calm. Not today, probably not in your lifetime. But the clock is running, and the universe has no obligation to warn you before it goes off. The gamma-ray burst scenario has a certain clean brutality to it. The beam arrives, the ozone breaks, the UV floods in, the food chain collapses, cause and effect drawn in straight lines across a few thousand light-years of empty space. It's terrifying, yes, but it's also simple. A flash from a dying star, aimed in the wrong direction at the wrong time. Bad luck on a cosmic scale. What makes it manageable, psychologically at least, is that it's over quickly. The star collapses once, the jet fires once, the damage unfolds over years, but the event itself is brief. 10 seconds, maybe a minute, and then it's done. The universe moves on. Black holes are not like that. Black holes don't collapse and disappear. They don't fire a beam and blink out. They sit, they wait, they grow. And they do it for billions of years without pause, without mercy, without anything remotely resembling an off switch. If a gamma-ray burst is a sniper rifle, a black hole is a slow gravitational whirlpool that never stops spinning and never runs out of things to pull under. And the largest ones, the supermassive black holes sitting at the centers of galaxies, are not just threats, they are architects. They shape the galaxies around them. They control the flow of matter across distances measured in thousands of light years. They regulate star formation, trigger quasars, and occasionally, when the mood strikes, they rip entire stars apart and eat them piece by piece while the rest of the galaxy watches. They are not invaders in the traditional sense. They were here first. But if one decided to move, If a supermassive black hole somehow got kicked out of its home galaxy and started drifting through space toward us, the Milky Way would not survive the encounter unchanged, and neither would we. Let's start with what a supermassive black hole actually is, because the name does not do the scale justice. A stellar mass black hole, the kind that forms when a massive star collapses, weighs somewhere between a few and a few dozen times the mass of our Sun. Supermassive black holes start at hundreds of thousands of solar masses and climb from there. The one sitting at the center of our own galaxy, Sagittarius A star, weighs roughly 4 million times the mass of the Sun. That's the local example, the well-behaved one, the one that mostly sits quietly in the middle of the Milky Way, occasionally snacking on a stray gas cloud or an unlucky star that wanders too close, but otherwise minding its own business. 4 million solar masses sounds extreme until you start looking at what else is out there. The supermassive black hole at the center of the galaxy Messier 87, the one famously photographed by the Event Horizon Telescope in 2019, weighs about 6.5 billion solar masses. The black hole at the center of the galaxy Holmberg 15A weighs roughly 40 billion solar masses. 40 billion. The number stops meaning anything at that scale. You can say it out loud, but your brain has no framework to process what 40 billion suns worth of mass compressed into a singularity actually represents. It's just a hole in space so massive that entire solar systems could orbit inside its event horizon and never touch the edges. Theoretical models suggest there's an upper limit to how big a supermassive black hole can grow through accretion, the process of pulling in gas and dust and matter from the surrounding environment. That limit sits somewhere around 50 billion solar masses. Beyond that point, the accretion disk, the swirling cloud of doomed material spiraling inward, becomes so energetic and so unstable that it stops feeding the black hole efficiently. Instead of falling in, the gas gets heated to such extreme temperatures that radiation pressure blows it outward, and the material that doesn't escape ends up forming stars in orbit around the black hole rather than crossing the event horizon. 50 billion solar masses is the point where a black hole becomes so powerful that it starts choking on its own growth. We haven't found one that large yet. The biggest confirmed supermassive black holes clock in around 40 billion, sitting right at the edge of what physics says should be possible. Which means we are living in a universe where the largest gravitational monsters allowed by the rules have already formed and are currently sitting at the centers of distant galaxies, quietly holding court over billions of stars. The question that keeps astrophysicists awake is not whether supermassive black holes exist. We've seen them, we've photographed them, we've measured their masses by watching stars orbit around them at ridiculous speeds. The question is how they got so big, so fast. Supermassive black holes exist in galaxies we're seeing as they were more than 12 billion years ago, less than a billion years after the Big Bang. One supermassive black hole with a mass of roughly 1 billion solar masses was detected in a galaxy whose light has been traveling toward us for over 12 billion years. We are seeing it as it existed when the universe was barely 700 million years old, still an infant by cosmic standards. A billion solar masses in 700 million years. Run the math on how fast a black hole can grow by eating gas and stars, and the timeline doesn't close. There is not enough time in the early universe to build something that massive starting from a stellar mass seed. The growth rate required is faster than the Eddington limit, the theoretical maximum rate at which a black hole can accrete matter before radiation pressure from the infalling material blows everything away. If you try to feed a black hole faster than the Eddington limit allows, the food fights back. The gas heats up, radiates energy, and gets pushed outward by its own light. The black hole can't eat. Growth stalls. And yet the supermassive black holes in the early universe clearly did not stall. They grew anyway, faster than they should have, larger than the models predicted, and no one has a fully satisfying explanation for how they pulled it off. There are two leading ideas, and both require the universe to have taken shortcuts. The first idea is that the initial seeds were much larger than anyone assumed. Instead of starting from stellar mass black holes weighing a few dozen suns, maybe the first supermassive black holes formed directly from the collapse of enormous gas clouds in the early universe. Clouds weighing tens of thousands or even hundreds of thousands of solar masses that skipped the star formation step entirely and collapsed straight into black holes. If you start with a seed that's already 100,000 solar masses, you've got a massive head start. Grow from there at the Eddington limit and you can reach 1 billion solar masses within the available time. The problem is that we've never observed a gas cloud collapsing directly into a black hole. It's theoretically possible under very specific conditions: early universe, low metallicity, no nearby stars to disrupt the collapse, but it's never been confirmed. The second idea is that black holes in the early universe somehow fed faster than the Eddington limit allows. Maybe the gas was denser. Maybe the magnetic fields were different. Maybe the geometry of the accretion disks allowed for bursts of super-Eddington accretion that current models don't account for. If that's true, then the rules we think govern black hole growth are incomplete, and the early universe was a wilder place than we've given it credit for. Either way, the result is the same. By the time galaxies were 1 billion years old, they already had supermassive black holes weighing billions of solar masses sitting at their centers. And those black holes have been growing ever since. Not steadily, not smoothly. Black holes don't eat on a schedule. They eat when there's food available, and in a galaxy, food means gas, dust, and stars. Most of the time, the region around a supermassive black hole is relatively quiet. The nearby stars are in stable orbits. The gas has either fallen in already or been blown away by previous feeding episodes. The black hole sits dormant, invisible except for the gravitational influence it exerts on everything around it. Then something changes. Two galaxies collide, and the merger sends shockwaves of gas tumbling toward the centers of both galaxies. Or a giant molecular cloud drifts too close and gets captured by the black hole's gravity. Or a star wanders into the wrong orbit and gets torn apart by tidal forces, its guts scattered into a thin stream that spirals inward. When that happens, the black hole wakes up. And when a supermassive black hole wakes up, it doesn't whisper, it screams. The gas falling toward a supermassive black hole doesn't fall straight in, it spirals. The black hole is rotating, and the space around it is twisted by that rotation, dragged along like water circling a drain. The infalling gas settles into a flat disk, an accretion disk, where it orbits the black hole at speeds approaching a significant fraction of light speed. Friction between particles in the disk heats the gas to millions of degrees. At those temperatures, the gas doesn't just glow. It radiates across the entire electromagnetic spectrum. X-rays, ultraviolet, visible light, infrared, radio waves, all pouring out from a region that can be smaller than our solar system, but brighter than an entire galaxy of hundreds of billions of stars. This is what astronomers call an active galactic nucleus, and it's one of the most luminous phenomena in the universe. When a supermassive black hole is actively feeding, the energy output can reach trillions of times the luminosity of our sun. Trillions, from an object that by itself emits no light at all. The light is coming from the matter dying on its way in, heated to such extremes by friction and compression that it glows brighter than anything else in the local universe before finally crossing the event horizon and vanishing forever. Some of these active galactic nuclei are so bright that we've given them a special name. We call them quasars, short for quasi-stellar objects, because when they were first discovered in the 1960s, they looked like stars in photographs, but had spectra that made no sense. They were far too bright and far too distant to be stars. It took years to figure out what they actually were. Supermassive black holes in the centers of distant galaxies, feeding so aggressively that they outshine every star in the galaxy combined. The nearest quasars are billions of light-years away. The farthest ones we've detected are over 13 billion light-years out, meaning we're seeing them as they existed less than a billion years after the Big Bang. And even from that distance, even after traveling across more than 90% of the observable universe, the light from those quasars is still bright enough to show up in our telescopes. If you could somehow place a quasar at the distance of the nearest star to our Sun, roughly 4 light-years away, it would appear brighter in the sky than the full moon. From 4 light-years, a supermassive black hole eating gas in another galaxy, 13 billion light-years away, produces enough light to be visible as a point source in our sky. That's not a minor detail. That's a fundamental statement about how much energy these objects release when they're active. And some of them point at us. When a supermassive black hole is feeding, it doesn't just radiate light in all directions. The intense magnetic fields around the accretion disk can focus some of that energy into narrow jets of particles that fire outward along the rotational axis of the black hole at nearly the speed of light. These jets can extend for thousands of light-years, punching through the surrounding gas and carving tunnels in the intergalactic medium. If one of those jets happens to be aimed directly at Earth, the object becomes what astronomers call a blazar. A blazar looks like an extraordinarily bright, rapidly variable point of light in the sky. The brightness can change on timescales of hours or days as the jet flickers and pulses. The energy output across all wavelengths is staggering. Blazars emit gamma rays, X-rays, ultraviolet, visible light, infrared, and radio waves simultaneously, all coming from a jet of particles moving so close to light speed that relativistic effects boost the apparent brightness by orders of magnitude. The jet is already absurdly luminous. Relativistic beaming makes it look even brighter. From Earth, a blazar is one of the most energetic things you can point a telescope at without looking directly at a gamma-ray burst. The existence of quasars and blazars tells us something important about supermassive black holes. They are not passive objects. They do not sit quietly in the background. When conditions are right, when there's enough gas available to feed them, they become the dominant source of energy in their host galaxies. And that energy doesn't just radiate outward harmlessly into space, it affects everything around it. The jets from a supermassive black hole can heat the surrounding gas to temperatures so high that it can't cool down and collapse to form new stars. The radiation from the accretion disk can ionize gas clouds hundreds or thousands of light-years away, stripping electrons from atoms and preventing molecular clouds from forming. Supermassive black holes regulate star formation in their host galaxies. They act as thermostats, controlling how much gas is available for making new stars and how fast the galaxy can grow. This is called feedback, and it's one of the reasons galaxies don't just keep forming stars forever until they run out of gas. The supermassive black hole at the center turns on periodically, blasts the surrounding environment with energy, and shuts down star formation until things cool off again. The cycle repeats. Galaxies and their central black holes co-evolve. The mass of the black hole is correlated with the mass of the galaxy's central bulge. Bigger galaxies have bigger black holes, not because the black hole ate the galaxy. The black hole is a tiny fraction of the galaxy's total mass, but because the two grew together, feeding off the same reservoir of gas, influencing each other's development over billions of years. Now imagine a supermassive black hole leaving its galaxy, not by choice. Black holes don't have agency, but through circumstance. Two galaxies collide, a common event in the universe, and the supermassive black holes at their centers spiral toward each other, drawn together by gravity. If the two black holes have similar masses, they eventually merge, forming a single larger black hole and releasing a burst of gravitational waves in the process. But if the masses are unequal, or if the merger happens in a way that's not perfectly symmetric, the gravitational wave emission can be stronger in one direction than the other. Gravitational waves carry momentum. If the black hole emits more gravitational wave energy in one direction, it gets a recoil kick in the opposite direction. The black hole is flung outward like a cannonball fired from a gun made of space-time itself. The kick velocity can be hundreds or even thousands of kilometers per second. At those speeds, a supermassive black hole can escape its host galaxy entirely and become a rogue, a wandering singularity drifting through intergalactic space with nothing to stop it. This is not hypothetical. Astronomers have found candidates for recoiling supermassive black holes, objects that appear to be moving at high velocities relative to their host galaxies, trailing streams of gas and stars behind them as they plow through the surrounding medium. We haven't confirmed a case where a supermassive black hole has been completely ejected from its galaxy and is now traveling solo through the void. But the physics says it can happen, and the observations suggest it probably has. Which raises the question nobody wants to ask, but everyone has thought about. What happens if a rogue supermassive black hole enters the Milky Way? The first thing to understand is that a supermassive black hole passing through our galaxy would not be immediately lethal. It's not going to swallow the sun. It's not going to aim a jet at Earth and vaporize the atmosphere. A supermassive black hole is just a very massive object, and massive objects exert gravity. If a rogue black hole, weighing a few million solar masses, entered the Milky Way from outside, it would interact gravitationally with everything it passed. Stars near its path would have their orbits disrupted. Some would be flung outward at high velocities, ejected from the galaxy entirely. Others would be captured into orbits around the black hole, spiraling inward over time. Gas clouds near the intruder would be pulled toward it, heating up as they fell, potentially triggering a brief phase of accretion and turning the rogue black hole into a temporary quasar as it fed on Milky Way material. The gravitational disturbance would ripple outward, affecting star orbits across a wide region of the galaxy. The Milky Way's structure would change. The spiral arms might get disrupted. The central bulge could be altered, and, depending on where the rogue black hole passed, entire star clusters could be scattered or destroyed. The odds of Earth being directly affected are low. The Milky Way is enormous. 100,000 light-years across, containing hundreds of billions of stars, most of them separated by distances measured in light-years. A rogue black hole entering the galaxy is a serious event for the galaxy as a whole, but for any individual star system, the chances of a close encounter are vanishingly small. Space is mostly empty. Even when two galaxies collide, the stars almost never hit each other. They just pass by, their orbits rearranged by gravity, but the stars themselves untouched. A rogue supermassive black hole would do the same. It would pass through, alter some orbits, maybe capture a few stars, maybe trigger some star formation by compressing gas clouds as it moved, and then continue onward, leaving the Milky Way slightly more chaotic than it found it. Unless, of course, it didn't pass through, unless it got captured. If the rogue black hole's velocity and trajectory were just right, it could be captured by the Milky Way's gravity and settle into an orbit around the galactic center. And if that happened, it would eventually encounter Sagittarius A star, our own supermassive black hole. The two would spiral toward each other over millions of years, slowly losing energy to gravitational wave emission, their orbits decaying until they finally merged. The result would be a single larger supermassive black hole, weighing the combined mass of both, sitting at the center of the Milky Way, and in the final moments before merger, the event would release a burst of gravitational waves strong enough to be detected by instruments across the universe. LIGO, the Laser Interferometer Gravitational Wave Observatory, has already detected gravitational waves from merging stellar mass black holes dozens of times. A supermassive black hole merger would produce a signal thousands of times stronger. And if the merger happened in our own galaxy, the gravitational wave detectors on Earth would register the event as an unmistakable signal, a chirp in the data that would mark the moment two of the most massive objects in the Milky Way became one. None of this is happening right now. There are no rogue supermassive black holes on a collision course with the Milky Way that we know of. No intergalactic invaders barreling toward us at relativistic speeds. The nearest large galaxy to ours is Andromeda, roughly 2.5 million light-years away, and it's moving toward us, not away. In about 4 billion years, the Milky Way and Andromeda will collide, their stars passing through each other, their gas clouds smashing together and igniting bursts of star formation, and their supermassive black holes spiraling inward toward an eventual merger. That collision is already locked in. The gravitational attraction between the two galaxies is too strong to avoid, but 4 billion years is a long time. Long enough that the Sun will have aged noticeably by then, its luminosity increased enough that Earth's surface will be uncomfortably hot, possibly uninhabitable depending on how the climate and oceans respond. Long enough that if humanity or whatever species evolves from us is still around, we will have had plenty of time to see it coming and figure out what to do about it. The Andromeda collision is not a surprise. It's a scheduled event. What keeps the supermassive black hole scenario unsettling is not the immediacy, it's the scale. Gamma-ray bursts are terrifying because they're fast and lethal. Supermassive black holes are terrifying because they're slow and inevitable. They sit at the centers of galaxies, shaping the environments around them, regulating star formation, triggering quasars, and occasionally tearing stars apart when one wanders too close. They grow over billions of years. They merge when galaxies collide. And in the far future, when galaxies have finished merging into larger and larger structures, the supermassive black holes at the centers of those structures will grow even larger, potentially reaching masses of 10 to the 14th solar masses during the collapse of superclusters billions of years from now. At that point, the universe will be old and cold, most stars will have burned out, and the dominant objects in the cosmos will be black holes, slowly accreting the last scraps of available matter and radiating away their mass through Hawking radiation over timescales so long that the current age of the universe is a rounding error by comparison. We're not there yet. The universe is still young. Stars are still forming. Galaxies are still colliding. And supermassive black holes are still waking up, feeding, shining as quasars, and shaping the structure of the cosmos. They are not invaders in the sense of arriving from outside. They are part of the architecture. But they are invaders in the sense that they pull in gas, they disrupt star orbits, they tear apart anything that gets too close. And they do it with a patience and a scale that makes every other threat on this list look hurried by comparison. A gamma-ray burst is over in seconds. A supermassive black hole is forever, or at least it's forever on any time scale a human mind can wrap itself around. And somewhere out there, drifting through the space between galaxies, or sitting quietly at the center of a distant spiral, one of them is waiting. Not for us, not specifically, but waiting nonetheless, as black holes do, for the next meal to arrive. Black holes are patient. They sit, they wait, they grow over timescales that make human history look like a sneeze. But stars? Stars are different. Stars burn fast when they're massive enough, and when they run out of fuel, they don't fade quietly into the cosmic background, they detonate. And the biggest ones, the true monsters at the upper end of the mass scale, don't just explode, they hyper-explode. They release so much energy in such a short span of time that the word supernova stops being adequate. Astronomers had to invent a new term to describe what happens when a star, weighing more than 30 times the mass of our Sun, reaches the end of its life and decides to take a significant chunk of the surrounding space-time with it. They call it a hypernova. And if you thought gamma-ray bursts were bad, you need to understand that hypernovae are what produce most of the long-duration gamma-ray bursts in the first place. The hypernova is the engine, the gamma-ray burst is the exhaust, and the exhaust alone is enough to sterilize a planet from thousands of light-years away. Let's start with what a normal supernova looks like, because hypernovae only make sense when you understand what they're exceeding. There are two main types of supernova, and they have nothing in common except the name and the fact that both involve stars exploding. Type 1, a supernovae happen in binary star systems where a white dwarf, the dense cooling remnant of a sun-like star, is siphoning matter off a companion star. The white dwarf grows heavier. When it crosses a threshold called the Chandrasekhar limit, roughly 1.4 times the mass of our Sun, the pressure and temperature in its core trigger runaway carbon fusion. The entire star detonates in a thermonuclear explosion so uniform and so predictable that astronomers use Type 1a supernovae as standard candles to measure cosmic distances. Every Type 1a supernova releases roughly the same amount of energy, about 10 to the 44th joules, and shines with the same peak brightness. See one, and you know how far away it is based on how dim it looks from Earth. These explosions are violent, bright enough to briefly outshine entire galaxies, but they're not the kind that lead to gamma-ray bursts. White dwarfs are too small and too slow. They don't have the mass or the spin to form jets. They just blow apart, scatter their guts into space, and leave nothing behind. Type 2 supernovae are different. These are core collapse events. They happen when massive stars, anything above about 8 solar masses, burn through their fuel and reach the point where the core is filled with iron. Iron doesn't fuse into heavier elements in a way that releases energy. Fusing iron costs energy. So when the core runs out of lighter elements to burn, fusion stops. The outward pressure that has been holding the star up against its own gravity disappears. The core collapses. In less than a second, a ball of matter the size of a small planet, weighing more than the Sun, gets crushed down into a sphere roughly 20 kilometers across. The collapse releases an enormous amount of gravitational potential energy, most of it in the form of neutrinos that blast outward through the star. The outer layers, which have been falling inward, hit the newly formed neutron star core and rebound. The rebound sends a shock wave racing outward through the star. The shock wave reaches the surface and the star explodes. A Type II supernova. The explosion releases about 10 to the 44th joules, the same order of magnitude as a Type Ia, but the mechanism is completely different. This one leaves a remnant behind, either a neutron star if the core is below about 3 solar masses, or a black hole if it's heavier. Type II supernovae are what seed the galaxy with heavy elements. Carbon, oxygen, silicon, iron, all the atoms heavier than helium that make up planets and people were forged inside massive stars and scattered into space when those stars went supernova. We are made of star guts. That's not poetry, that's nucleosynthesis. Now take a Type II supernova and scale it up, way up. Make the star more massive, 40 solar masses, 50, 60. Give it something most stars don't have: rapid rotation, strong magnetic fields. When a star like that collapses, the core doesn't just form a neutron star, it forms a black hole almost immediately. But the collapse doesn't stop the outer layers from falling inward, and the rotation means the infalling material doesn't fall straight in. It spirals. The magnetic fields, already strong, get amplified by the collapse. Simulations show that turbulence in the collapsing star creates a dynamo effect, a feedback loop where motion and magnetism reinforce each other until the magnetic field strength reaches 10 to the 15th times the strength of Earth's magnetic field, 10 to the 15th. At those field strengths, the magnetic field lines twist into a configuration that channels energy into two narrow beams along the star's rotational axis. The beams punch through the collapsing star, break into open space, and fire outward at 99% the speed of light, carrying hard stellar material and gamma radiation. This is a hypernova, and the kinetic energy released is not 10 to the 44th joules, it's 10 to the 45 joules, 10 times higher. Some hypernovae go even further. The kinetic energy can exceed 10 to the 52 ergs, which translates to more than 10 to the 45 joules, depending on how you count. The explosion is so energetic that the spectral lines in the light we observe from the expanding debris are unusually broad, a signature of material moving at extreme velocities. The star doesn't just explode, it shreds itself. The first confirmed hypernova was detected in 1998. The object was designated supernova 1998 BW, and it was unusual from the moment astronomers started analyzing the data. The luminosity was 100 times greater than a standard Type 1b supernova, a subclass of core collapse events where the star has lost its hydrogen envelope before exploding. 100 times. That's not a measurement error. That's a different category of event. The spectrum showed signs of material moving at velocities that normal supernovae don't reach, and within hours of the explosion, a gamma-ray burst was detected from the same location. The connection was undeniable. This was not just a supernova, it was the engine that produced a gamma-ray burst. Supernova 1998 BW was the smoking gun that confirmed what theorists had been predicting. Long-duration gamma-ray bursts, the ones lasting more than 2 seconds, come from hypernovae. The hypernova is the explosion. The gamma-ray burst is the jet. If the jet points at Earth, we see the burst. If it points somewhere else, we just see an unusually bright supernova with strange spectral features and no gamma rays. Same event, different viewing angle. The term hypernova was coined in the late 1990s by astronomers Stan Woosley and Shigeru Iwamoto, both of whom had been working on models of massive star death for years. They needed a word to describe explosions that were clearly more energetic than normal supernovae, but didn't fit neatly into the existing classification schemes. Hypernova stuck. It's not an official term in the way Type 1a or Type 2 is, but it's widely used, and everyone knows what it means. An exploding star on steroids, a core collapse event so violent that it produces jets, forms a black hole, and releases enough energy to be detected across billions of light-years. A truly insane occurrence, to borrow a phrase from one particularly blunt video essayist whose name has been lost to the YouTube algorithm but whose tone was unmistakable. Hypernovae are rare. The Milky Way produces roughly one supernova every 50 years on average, but only a small fraction of those are core collapse events from stars massive enough to go hypernova. Estimates vary, but the current best guess is that our galaxy produces about one long-duration gamma-ray burst, and therefore one hypernova every 10,000 to 1 million years. The uncertainty is large because we can't see most of our own galaxy. Dust blocks visible light. Stars closer to the galactic center are hidden behind layers of gas and other stars. We rely on infrared and radio observations to map the Milky Way's structure, and those observations are incomplete. What we do know is that hypernovae are rare enough that you're unlikely to see one in your lifetime, but common enough over geological timescales that Earth has almost certainly been exposed to several during its history. And if one of those events occurred close enough and aimed the jet at us, the results would show up in the fossil record as an extinction boundary. Some researchers think that's exactly what happened. A paper published by a team that included scientists from NASA and the University of Kansas suggested that a nearby hypernova, or more specifically the gamma-ray burst it produced, may have triggered the Ordovician Silurian extinction event roughly 440 million years ago. The evidence is circumstantial. There's no isotopic smoking gun like the iridium layer that marks the asteroid impact that killed the dinosaurs. But the pattern fits. The extinction happened in two pulses. The second pulse coincides with evidence of rapid climate change and shifts in ocean chemistry. Marine species, particularly those living in shallow water, were hit hardest. Around 60% of marine species disappeared. That's consistent with ozone depletion and a spike in ultraviolet radiation, exactly what you'd expect from a nearby gamma-ray burst. The mechanism works, the timing works, the victims fit. What's missing is proof. And in the absence of proof, the hypothesis remains open, tantalizing, and uncomfortably plausible. The thing about hypernovae is that they don't need to be especially close to cause problems. A hypernova occurring within 6,000 light-years aimed at Earth would strip a significant fraction of the ozone layer and flood the surface with ultraviolet radiation. At that range, the gamma-ray burst itself, the direct radiation from the jets, is what does the damage. Closer in, within a few hundred light-years, and you start worrying about the kinetic energy. The explosion sends a shockwave of particles, mostly protons and heavier nuclei, racing outward at a significant fraction of light speed. These are cosmic rays, and they're dangerous. Cosmic rays hitting the atmosphere generate secondary particles that can reach the surface. High-energy cosmic rays can damage electronics. They can induce mutations in living cells. A nearby hypernova would increase the cosmic ray flux at Earth by orders of magnitude for years after the explosion. The ozone layer would be gone, the ultraviolet would be lethal, and on top of that, the cosmic ray dose would climb high enough to cause direct biological harm. It's not just one threat, it's a cascade. Fortunately, there are no hypernova candidates within a few hundred light-years. The nearest massive stars capable of going hypernova are farther out, well beyond the immediate kill zone, but several sit within the 6,000 light-year range where a poorly aimed jet could still cause an extinction-level event. Wolf-Rayet 104, mentioned earlier, is one. Eta Carinae, roughly 7,500 light-years away, is another. Both are massive, both are unstable, and both are the kind of stars that could theoretically produce hypernovae when they collapse. The jets are narrow, the odds are low, but the jets exist, and if one of them swings past Earth, the fact that it was statistically unlikely won't matter. The ozone will still break, the ultraviolet will still flood in, and the fossil record will mark another boundary where something went catastrophically wrong. There's a related class of objects that deserves mention because they occupy a similar threat category, but come from a slightly different origin: magnetars. These are neutron stars, the kind that form when a massive star collapses but doesn't quite make a black hole. Neutron stars are already extreme. Take 1.4 solar masses and crush it into a sphere 20 kilometers across. The density is so high that a teaspoon of neutron star material would weigh 1 billion tons. Gravity at the surface is 200 billion times stronger than on Earth. The escape velocity is about 1/3 the speed of light. Neutron stars are, by any measure, the densest stable objects in the universe. Magnetars are neutron stars with magnetic fields so strong that they break physics as we normally understand it. The field strength can reach 10 to the 15th Gauss. For comparison, Earth's magnetic field is about half a Gauss. A strong refrigerator magnet is about 100 Gauss. An MRI machine runs at about 30,000 Gauss. A magnetar's magnetic field is 10 trillion times stronger than an MRI. At those field strengths, the vacuum itself becomes polarized. Light passing through the magnetar's magnetosphere gets bent. Atoms get stretched into thin, elongated shapes. If you were standing on the surface of a magnetar, assuming you could somehow survive the gravity, the magnetic field would rip the electrons out of your atoms and turn you into a cloud of ionized plasma before you had time to register discomfort. Magnetars occasionally have what astronomers politely call outbursts. The magnetic field lines, twisted into unstable configurations by the neutron star's rotation and internal dynamics, suddenly snap and reconnect. The reconnection releases energy, a lot of energy. In December 2004, a magnetar designated soft gamma repeater 1806-20 underwent an outburst that was detected by satellites across the solar system. The burst lasted 1/10 of a second. In that 1/10 of a second, the magnetar released more energy than the Sun produces in 100,000 years. The burst was so intense that it ionized Earth's upper atmosphere from 50,000 light-years away. 50,000 light-years. The magnetar was in another part of the galaxy, nowhere near us, and the burst still reached across half the Milky Way and measurably altered the ionosphere. If the same event had occurred within 10 light-years, the radiation dose at Earth's surface would have been high enough to cause immediate harm. At 1 light-year, it would have been lethal. Magnetars don't aim their bursts the way hypernovae aim gamma-ray bursts. The energy radiates more or less evenly in all directions, but the sheer power output means they don't need to aim. Get close enough, and the ambient radiation is deadly on its own. There are about a dozen confirmed magnetars in the Milky Way, and possibly a few dozen more that haven't been identified yet because they're not currently active. Most of them are thousands of light-years away. None of them are close enough to worry about. But magnetars are young objects. They form in supernova explosions, and the magnetic field decays over time. A magnetar is only a magnetar for a few thousand years before the field weakens and it becomes an ordinary neutron star. That means the magnetars we see today formed recently, geologically speaking, and there have been many more in the past. Some of them formed closer to Earth. Some of them went through their outburst phase when complex life was just getting started. And some of those outbursts, if they were strong enough and close enough, may have left marks. We haven't found them yet. The fossil record doesn't preserve magnetic field signatures, but the possibility sits there, quiet and uncomfortable, in the same category as nearby gamma-ray bursts and hypernova jets. Rare, distant, probably fine, but not impossible. Then there are the smaller threats, not extinction level, not even close, but worth mentioning because stars don't need to explode to cause problems. Our own sun produces flares and coronal mass ejections on a regular basis. A solar flare is a sudden release of magnetic energy from the sun's surface, usually associated with sunspots and active regions where the magnetic field is tangled. The flare releases radiation across the electromagnetic spectrum, from radio waves to X-rays. Most of it gets absorbed by Earth's atmosphere and magnetosphere. Occasionally, a flare is strong enough to disrupt radio communications and damage satellites. A coronal mass ejection is worse. This is a massive burst of plasma and magnetic field ejected from the sun's corona, the outer atmosphere. If a coronal mass ejection hits Earth directly, it compresses the magnetosphere, induces currents in power grids, and can knock out electrical infrastructure over large areas. The Carrington event in 1859 was a coronal mass ejection so strong that telegraph systems caught fire and auroras were visible as far south as the Caribbean. If the same event happened today, the damage to satellites, power grids, and communication networks would run into the trillions of dollars, and that was our sun. A middle-aged, stable, well-behaved G-type star. Now imagine a young, active star, something hotter and more massive, sitting close enough that its flares reach Earth with significant energy. Most stars in the solar neighborhood are smaller and cooler than the sun. Red dwarfs, M-type stars, the most common stars in the galaxy. They flare constantly. A red dwarf flare can increase the star's brightness by several times its normal output for minutes or hours. If Earth orbited a red dwarf at the distance where liquid water could exist, the planet would be tidally locked, one side always facing the star, the other in permanent darkness, and the flares would hit the day side with enough energy to strip the atmosphere over millions of years. This is why most astrobiologists are skeptical that red dwarf planets can support life. The stars are too violent. The flares are too frequent. The habitable zone is too close. But red dwarfs are small. The sun is not. And even the sun occasionally produces flares strong enough to make us nervous. Other stars, especially young ones still settling into their main sequence lives, are worse. Tari stars, named after the prototype Tari in the constellation Taurus, are pre-main sequence stars, still contracting under gravity, not yet burning hydrogen steadily in their cores. They're surrounded by protoplanetary disks, clouds of gas and dust that will eventually form planets, but the stars themselves are chaotic. Magnetic fields tangle and snap, flares erupt constantly. Coronal mass ejections fire off in random directions. If Earth had formed around a T Tauri star, the early bombardment of radiation would have shaped the atmosphere in ways we can only guess at. Some researchers think frequent flares might actually help prebiotic chemistry by providing energy to drive chemical reactions in the atmosphere and oceans. Others think the flares would simply sterilize the surface and prevent life from getting started. The jury is still out. What's clear is that stars go through phases. Young stars are violent. Middle-aged stars, like the sun, are calmer. Old stars, red giants, are unstable in a different way. The outer layers puff up and the core contracts. The star becomes a variable, its brightness fluctuating as the envelope pulses. Eventually, the outer layers drift away, leaving a white dwarf behind. But during the red giant phase, if you happen to be orbiting too close, the expanding envelope swallows you. Earth will be swallowed by the Sun in about 5 billion years when the Sun leaves the main sequence and becomes a red giant. The surface of the Sun will expand past Earth's current orbit. The planet will spiral inward, dragged by friction with the Sun's outer atmosphere, and eventually vaporize. That's not a maybe, that's a certainty. The only question is whether Earth gets swallowed before the Sun sheds enough mass that Earth's orbit expands outward and escapes. Current models suggest swallowing is more likely. Either way, Earth's time as a habitable planet ends long before the Sun becomes a red giant. The Sun's luminosity increases slowly over its main sequence lifetime. In about 1 billion years, the increased heat will evaporate the oceans. In 2 billion years, the surface will be Venus-like, hot and dry and lifeless. The Sun doesn't need to explode to kill us, it just needs to age. Massive stars don't have that luxury. They burn fast. A star weighing 50 solar masses might only live a few million years from birth to supernova. There's no slow, graceful decline. The star ignites, burns hydrogen into helium in its core, exhausts the hydrogen and starts burning helium into carbon. Exhausts the helium and starts burning carbon into oxygen. The fusion progresses through heavier and heavier elements, neon, magnesium, silicon, until the core is full of iron. Each stage burns faster than the last. Hydrogen burning lasts millions of years. Silicon burning lasts a few days. When the core is iron, fusion stops. The clock runs out. The star has minutes left, maybe hours if it's on the lower end of the mass range. The core collapses, the hypernova begins. And the star that spent millions of years growing, fusing elements, shaping the surrounding space with its radiation and stellar wind, ends in a flash of light, bright enough to be seen across the universe. That's the life cycle. Birth, fusion, collapse, death. For massive stars, death is not a quiet fade, it's a hypernova. And if you're close enough when it goes off, death is contagious. We live in a universe where stars explode. That's not optional. It's part of the structure. Stars form from collapsing gas clouds. They burn their fuel. They die. Some fade quietly. Some explode. And a few, the most massive ones, the ones unlucky enough to be born with enough mass to collapse all the way to a black hole, explode so violently that they produce jets of gamma radiation traveling at near light speed, aimed at random directions, capable of causing extinction events across thousands of light years. This has happened before. It will happen again. The only question is when and where and whether the geometry lines up in a way that matters to us. For now, the nearby massive stars are stable. The magnetars are far away. The Sun is middle-aged and calm, but stability is temporary. Stars evolve, galaxies collide. And the universe does not care whether you're ready when the next hypernova goes off. It's already on its way. You just don't know which star yet. And neither does anyone else. Because the thing about hypernovae is that there's no warning. One day the star is there, burning steadily, minding its own business. The next day it's gone, and a jet of gamma radiation is racing outward at the speed of light, carrying more energy than the Sun will produce in its entire lifetime, aimed at some random patch of sky where something, maybe a planet, maybe a moon, maybe a whole solar system full of life, is about to learn what it means to be in the wrong place at the wrong time. And somewhere in that expanding shell of debris, mixed in with the gas and dust and newly forged elements, are the building blocks of future planets, future stars, future life. Because the universe is efficient, it recycles. The death of one star seeds the birth of others. The hypernova that sterilizes one world provides the carbon and oxygen and iron that another world will use to build continents and oceans, and eventually, if the chemistry works out, something that can look up at the sky and wonder what else is out there. That's the trade. Death feeds life. Explosions build galaxies. And every atom in your body, every molecule of water you drink, every breath you take, came from a star that died violently enough to scatter its guts across light years of space. You are made of hypernova debris. That's not metaphor, that's nucleosynthesis. And the star that made you has long since vanished, its light faded, its remnant cooled, its location forgotten. But somewhere out there, another massive star is burning through its fuel, racing toward the moment when the core fills with iron and the clock runs out. And when it goes, when the hypernova fires and the jets ignite and the gamma rays scream outward into the void, something will be in the path. Maybe nothing important, maybe a lifeless rock, maybe a comet, maybe a planet full of curious organisms pointing telescopes at the sky, mapping distant galaxies, calculating the odds, and assuming quietly that the universe will give them just a little more time before the lights go out. Hypernovae fire jets, magnetars unleash bursts, supermassive black holes tear stars apart and broadcast the destruction across thousands of light years. Those are threats you can see coming, at least in principle. They shine, they radiate. They leave signatures in the electromagnetic spectrum that telescopes can detect and analyze. You point an instrument at the sky, collect photons, run the numbers, and if you're lucky, you get a warning. Not much of one, granted. Gamma rays travel at light speed. By the time you see them, they've already arrived. But at least there's light. At least there's something to look at. Rogue planets don't give you that courtesy. They don't burn. They don't fuse hydrogen in their cores. They don't have accretion disks or jets or magnetic fields strong enough to rip apart passing spacecraft. They're just rocks, big ones. Jupiter-sized, Earth-sized, sometimes bigger, sometimes smaller, drifting through interstellar space in total darkness, invisible to every telescope we've ever built unless they happen to pass directly in front of a background star and block its light for a few hours. They are the universe's least considerate houseguests. They show up unannounced, stay as long as they want, and if one decides to wander into the solar system, the first sign you'd have is when the orbits start shifting. By then, it's already too late to do anything except watch the math play out. The term rogue planet is slightly misleading because it implies intent. Planets don't go rogue in the sense of making a conscious decision to leave. They get kicked, or they form alone. Either way, the result is the same. A world with no sun, no heat, no light. Just a frozen lump of rock or gas drifting through the void at tens of kilometers per second, following whatever trajectory was set when it left its birthplace millions or billions of years ago. Some were ejected from their home systems by gravitational interactions with other planets or passing stars. Some never had a home system to begin with. They condensed directly from collapsing gas clouds, the same way stars form, but without enough mass to ignite fusion. Failed stars. Orphaned worlds. The galaxy is full of them, and the numbers are staggering. Current estimates suggest the Milky Way contains roughly 2 trillion rogue planets. 2 trillion. For context, the Milky Way contains somewhere between 100 billion and 400 billion stars, depending on which survey you trust. That means rogue planets outnumber stars by a factor of at least 6 to 1. For every sun in the galaxy, there are 6 worlds wandering alone in the dark. Some estimates go higher. A study published in 2021 suggested there could be as many as 20 rogue planets for every star. 20. If that number holds, the Milky Way is less a collection of solar systems and more a sea of untethered worlds with a few lit-up patches where stars happen to be shining. We didn't know any of this until recently. The first confirmed rogue planets were discovered in the year 2000 using infrared telescopes pointed at young star-forming regions. The objects were too dim to be stars, but too massive to be anything else. They weighed more than 13 times the mass of Jupiter, the rough cutoff point between planets and brown dwarfs. Brown dwarfs are failed stars that started to fuse deuterium in their cores, but never got hot enough to ignite hydrogen. They glow faintly in the infrared. Rogue planets below the 13 Jupiter mass threshold don't even do that. If they're old enough, they're completely dark. The only reason we found the first batch is because they were young, still warm from their formation, radiating leftover heat in wavelengths that infrared detectors could pick up. Older rogue planets are effectively invisible. You can't see them. You can only infer their existence when they drift in front of something brighter and block the light. That's where gravitational microlensing comes in. Einstein's general relativity predicts that massive objects bend spacetime, and light traveling through that curved spacetime follows the bend. If a rogue planet passes between Earth and a distant star, the planet's gravity acts like a lens, briefly magnifying the star's light. The effect lasts anywhere from a few hours to a few days, depending on the planet's mass and how fast it's moving. The star brightens, peaks, dims, and returns to normal. The shape of the brightness curve tells you the mass of the lensing object. If the mass is in the planetary range, you've just detected a rogue planet. The technique works, but it's brutally inefficient. You need to monitor millions of stars continuously and hope that one of them happens to align with a passing rogue planet during your observation window. Most microlensing events happen once and never repeat. The rogue planet drifts on, the star returns to its baseline brightness, and you're left with a single data point confirming that somewhere out there, a planet-sized object passed through your line of sight and will never be seen again. Despite the challenges, microlensing surveys have found dozens of rogue planet candidates over the past 2 decades. Some are Jupiter mass, some are smaller. A few detections suggest objects as small as a few Earth masses drifting alone between the stars. The smallest confirmed candidates weigh around 0.3 Earth masses. That's smaller than Venus. A world that size, wandering through interstellar space, is cold enough that any atmosphere it once had has frozen solid and fallen to the surface as snow. The surface itself would be a featureless plain of ice, undisturbed by wind or weather, dark enough that standing on it would feel less like being on a planet and more like being inside a sensory deprivation tank with gravity. In December 2021, astronomers announced the largest group of rogue planets ever detected. 70 to 170 objects, all floating in a star-forming region called the Upper Scorpius Association, roughly 400 light-years from Earth. The region is young, only a few million years old, which means the rogue planets there formed recently. They were either ejected from their natal systems almost immediately after formation, or they condensed in isolation from the start. The study that found them used data from multiple telescopes spanning 2 decades, combining observations from ground-based surveys and space telescopes to pick out faint infrared sources that didn't match known stars or brown dwarfs. The result was a population of objects ranging from roughly 5 to 10 Jupiter masses, all adrift, all alone, all clustered in the same region where stars are still forming. The implication is clear. Whatever process creates rogue planets is active right now in star-forming regions across the galaxy. We're watching it happen. There are two main formation scenarios, and both are supported by evidence. The first is ejection. Simulations run in the 1990s showed that young planetary systems are chaotic. Multiple planets form in overlapping orbits. Gravitational interactions between them are strong. Occasionally, one planet gets flung outward by a close encounter with another planet or with the host star. The ejected planet escapes the system entirely and becomes a rogue. Early solar system models suggest this happens frequently. For every stable planetary system like ours, there are probably several ejected planets wandering the galaxy, refugees from gravitational battles fought millions of years ago. Some researchers estimate that roughly 50% of all rogue planets formed this way, kicked out of their home systems during the chaotic early phases of planet formation. The second scenario is direct collapse. In this version, rogue planets never belonged to a star. They formed the same way stars do, from collapsing clouds of gas and dust. But the clouds were too small or too diffuse to ignite fusion. The result is a planetary mass object that condensed in isolation. For a long time, astronomers were skeptical that objects below about 5 Jupiter masses could form this way. The argument was that gas clouds smaller than that would dissipate before gravity could pull them together. Then the James Webb Space Telescope looked at the trapezium cluster in Orion and found objects as small as 0.6 Jupiter masses forming in isolation. 0.6. That's below the previous mass cutoff by almost an order of magnitude. The objects are there, they're forming, and they're doing it without a parent star anywhere nearby. The direct collapse scenario is real, which means a significant fraction of rogue planets, possibly the other 50%, never had a sun to begin with. Both formation paths produce the same end result: a planet drifting through interstellar space with no orbit, no heat source, no light. If the planet has a thick atmosphere, it might retain some internal heat for a while. Jupiter generates more heat than it receives from the sun, leftover warmth from its formation plus heat generated by gravitational contraction. A rogue planet the size of Jupiter would stay warm for tens of millions of years, maybe longer, before cooling to the point where even its cloud tops freeze. Earth-sized rogue planets don't have that luxury. They cool fast. Within a few million years, the surface temperature drops to near absolute zero. Any water on the surface freezes solid. Any atmosphere thick enough to trap heat eventually condenses and falls as ice. What's left is a frozen tomb, dark and silent, hurtling through space at tens of kilometers per second. Interestingly, some rogue planets aren't completely dead. 6 out of 8 observed rogue planets in the 5 to 10 Jupiter mass range show infrared signatures consistent with warm, dusty disks surrounding them. That means they're not just planets. They're planets with their own mini-solar systems. Gas and dust orbit these rogue worlds, heated by the planet's residual warmth, possibly forming smaller moons or even rocky bodies in orbit around the rogue planet itself. The disks emit radiation from silicon grains, the same kind of emission seen around young stars with protoplanetary disks. A rogue planet with a disk is not just an orphaned world. It's a tiny solar system in its own right, wandering the galaxy, spawning its own satellites, completely independent of any star. That's not something anyone predicted. It's also deeply weird and raises uncomfortable questions about how far down the ladder of self-sufficient systems you can go before the definition of solar system stops making sense. Then there's the issue of detection, which remains a nightmare. Microlensing works, but only for rogue planets that happen to pass in front of background stars we're already monitoring. Direct imaging works for young massive rogue planets that still glow in the infrared. Neither method works for old cold Earth-sized rogue planets drifting through the outer reaches of the galaxy. Those objects are completely dark. No light, no heat, no way to see them unless they physically block something brighter or pass close enough to a star that their gravity causes measurable perturbations. NASA's Nancy Grace Roman Space Telescope, scheduled to launch in 2027, is specifically designed to find rogue planets using microlensing. The mission is expected to detect hundreds of Earth mass rogues, possibly thousands, depending on how common they actually are. Until then, the census remains incomplete. We know rogue planets exist. We know there are trillions of them. We don't know where most of them are, or how fast they're moving, or whether any of them are on trajectories that intersect with the solar system. Which brings us to the part nobody wants to think about. What happens if a rogue planet enters the solar system? The short answer is, it depends on the mass, the velocity, and the trajectory. A small rogue planet, a few Earth masses, passing through the outer solar system at high speed might not do much. It would gravitationally perturb the orbits of distant objects in the Kuiper belt and Oort cloud, possibly sending a shower of comets inward toward the inner planets, but it wouldn't directly threaten Earth. A larger rogue planet, Jupiter mass or bigger, passing through the inner solar system is a different story. Jupiter's gravity is strong enough to alter the orbits of everything in the solar system if it were suddenly placed closer to the Sun. A rogue Jupiter drifting through the asteroid belt would scatter asteroids in all directions. Some would be flung outward into interstellar space. Others would be flung inward toward Earth, Mars, and Venus. The inner solar system would be hit by a bombardment lasting decades or centuries, depending on how many asteroids got redirected. Earth's orbit itself could shift, not by much, maybe a few percent, but enough to alter the climate. A slightly more elliptical orbit means hotter summers and colder winters. A slightly closer orbit means higher average temperatures. A slightly farther orbit means an ice age. The changes wouldn't happen overnight, but they would happen, and once a planet's orbit shifts, it doesn't shift back. The new orbit is permanent until something else comes along and shifts it again. If the rogue planet passed close enough, the effects get worse. A near miss within a few astronomical units could gravitationally strip part of Earth's atmosphere. Not all of it. Earth's gravity is strong enough to hold on to most of its air, but the upper layers, the exosphere, and parts of the thermosphere could be pulled outward by the rogue planet's gravity and lost to space. The immediate effects would be minimal. The lower atmosphere, where we live and breathe, would remain intact. But over time, the loss of the upper atmosphere would weaken Earth's magnetic shielding and increase exposure to solar wind. More solar wind means more atmospheric erosion over millions of years. Mars lost most of its atmosphere this way, though in Mars's case, the culprit was the solar wind itself, not a passing rogue planet. A close encounter with a massive rogue could accelerate the same process on Earth. A direct collision is the nightmare scenario, and fortunately, it's also the least likely. Space is big. The odds of a rogue planet's trajectory aligning perfectly with Earth's orbit at the exact moment Earth happens to be at that point in its orbit are vanishingly small. But vanishingly small is not zero. If a rogue planet the size of Earth hit Earth at typical interstellar velocities, tens of kilometers per second, the kinetic energy released would be comparable to the impact that formed the Moon 4.5 billion years ago. The collision would vaporize both objects. The debris would form a disk around the Sun. Some of it would eventually coalesce into a new planet or planets. Some would be flung out of the solar system entirely. Earth, as a habitable world, would cease to exist. Life would be over. Not gradually, not with time to adapt, instantly. One moment you're reading a video essay transcript about rogue planets. The next moment you're part of a rapidly expanding cloud of vaporized rock traveling at several kilometers per second. There would be no warning, no time to evacuate, no chance to build shelters or bunkers deep enough to survive. The impact energy is too high. Nothing survives. The odds of that happening in the next 1,000 years, according to researchers who have run the numbers, are about 1 in a billion. 1 in a billion is not comforting when the consequence is total annihilation, but it's low enough that it doesn't make the top 10 list of things that will probably kill us. Asteroid impacts are more likely. Supervolcanoes are more likely. Climate change is more likely. A nearby gamma-ray burst is more likely. Rogue planets are dangerous in the abstract, but in practical terms, the galaxy is so large and the solar system is so small, and the odds of a direct hit are so low that it ranks as a distant, theoretical concern rather than an immediate threat. That doesn't stop researchers from looking. Surveys like the Zwicky Transient Facility and the upcoming Vera the 100th Rubin Observatory are designed to catalogue fast-moving objects in the solar system, partly to track asteroids and comets, but also to catch anything unexpected drifting through. If a rogue planet entered the outer solar system, moving slowly enough that it got captured by the sun's gravity instead of passing straight through, we'd notice. The orbits of the outer planets would shift. Neptune's position would change measurably over the course of a few years. Pluto's orbit, already eccentric, would get even weirder. Observations of those shifts would tell us something massive was out there, even if we couldn't see it directly. At that point, the hunt would begin. Infrared telescopes would scan the outer solar system, looking for anything emitting even a faint heat signature. Radio telescopes would search for occultations, moments when the rogue planet passed in front of distant radio sources and blocked the signal. Eventually, we'd find it, and once we found it, we'd calculate its orbit and figure out whether it was going to stay or pass through. If it stayed, the solar system would have a new planet. If it passed through, we'd watch it leave and hope it didn't take anything important with it on the way out. There's a related class of objects worth mentioning because they've generated more public attention than rogue planets, despite being far less massive. Interstellar objects. These are asteroids or comets that originated in other solar systems and passed through ours on hyperbolic trajectories. Hyperbolic means they're moving faster than escape velocity. They come in, swing around the sun or one of the planets, and leave, never to return. The first confirmed interstellar object was Oumuamua, detected in October 2017 by the Pan-STARRS telescope in Hawaii. Oumuamua is Hawaiian for scout or messenger. The object was already leaving the solar system by the time we spotted it, moving at roughly 26 kilometers per second relative to the sun. Its shape was unusual, elongated, roughly 10 times longer than it was wide, like a cigar or a pancake depending on which model you trust. It didn't have a visible coma or tail, which meant it wasn't outgassing like a normal comet. But its trajectory showed a small non-gravitational acceleration, a slight push that couldn't be explained by the sun's gravity alone. Comets do this all the time. Outgassing from the surface as ice sublimates produces a tiny rocket effect that alters the orbit. Oumuamua appeared to be doing the same thing, but without visible outgassing. That inconsistency sparked a flurry of speculation. Some researchers suggested it was a hydrogen iceberg, a comet made of frozen hydrogen that sublimates invisibly. Others suggested it was a fragment of a shattered planet. A few suggested it was an artificial object, a solar sail or a probe sent by an alien civilization. That last idea got the most attention, mostly because it was the least likely and therefore the most interesting to talk about. No evidence supports the artificial hypothesis. Oumuamua behaves like a comet. It's shaped like an elongated asteroid or comet fragment. It accelerated like an outgassing comet. The fact that we couldn't see the outgassing doesn't mean it wasn't happening. It just means the gas was transparent or faint enough that our instruments missed it. The second confirmed interstellar object was Borisov, detected in August 2019 by amateur astronomer Gennady Borisov using a homemade telescope. Borisov is a comet, no ambiguity. It has a visible coma and tail. Its composition, analyzed spectroscopically as it passed through the inner solar system, closely matches comets from our own Oort cloud. Carbon monoxide, water, dust, all the usual ingredients. Borisov formed in another solar system, got ejected somehow, and wandered through interstellar space for millions or billions of years before drifting past the Sun. It didn't interact with anything. It just passed through, bright enough to observe for a few months, and then faded as it headed back into the void. Both objects are tiny. Oumuamua was probably a few hundred meters across. Borisov was roughly a kilometer. Neither posed any threat to Earth. They weren't on collision courses. Their trajectories took them through the outer solar system or the inner solar system, but nowhere near Earth's orbit at a time when Earth was nearby. The interesting part is that they exist at all. If interstellar objects are common enough that we've detected two in the span of 2 years using ground-based telescopes that weren't specifically designed to find them, then there are probably many more passing through the solar system at any given time. Most are too small or too far away to spot. A few are large enough to detect if we're looking in the right place at the right time. None of them are rogue planets. Rogue planets are much larger, much rarer, and much harder to detect unless they pass directly in front of a star or get close enough that their gravity causes measurable effects. The broader point is that interstellar space is not empty, it's full of stuff. Rogue planets, interstellar comets, asteroids ejected from other solar systems, clouds of gas and dust between the stars. Most of it is invisible. Most of it will never come close to Earth. But the sheer number of objects out there, trillions of rogue planets alone, means the odds of an encounter are non-zero. Low, yes. Non-zero, also yes. And the difference between those two words is the only reason we're not currently tracking a Jupiter-sized intruder plowing through the Kuiper belt and scattering icy bodies toward the inner planets. For now, the solar system is stable. The planets orbit in predictable paths. The asteroids stay in the asteroid belt. The comets stay in the Oort cloud unless something nudges them inward. No rogue planets have entered the system in recorded history. No interstellar objects have hit Earth. The sky is calm, but calm is not permanent. The galaxy is full of wandering worlds, most of them dark, all of them moving, some of them on trajectories that will eventually bring them through this neighborhood. When that happens, if the mass is large enough and the trajectory is close enough, the solar system will change, orbits will shift, objects will be scattered, and somewhere on Earth, astronomers will point their telescopes at the sky, collect the data, run the calculations, and realize that the stable, predictable solar system they've been mapping for centuries just became a little less predictable. That moment hasn't arrived yet. The rogue planets are still out there, drifting in the dark, invisible and unreachable, but they're moving, and the galaxy is patient. Sooner or later, one of them will pass close enough to matter. You won't see it coming. There's no light to warn you. Just a slow shift in the numbers as the orbits start to drift and the asteroids begin falling inward. And by the time anyone notices, the intruder will already be here. Rogue planets drift through the void in silence, invisible until they're close enough to ruin your day. They're dangerous in the abstract, terrifying in theory, but statistically unlikely to show up in your lifetime or your grandchildren's lifetimes or anyone's lifetime for the next few thousand generations. The thing about rogue planets is that they're rare visitors. They come from outside. They don't belong here. Asteroids and comets, on the other hand, are already here. They've always been here. They're part of the solar system's original furniture, leftovers from the construction process that built the planets 4.5 billion years ago. And unlike rogue planets, which might pass through once in a few million years if you're unlucky, asteroids and comets are constantly wandering through the inner solar system. Most of them miss. A few don't, and when they don't miss, the results show up in the geological record as boundary layers, where everything below is thriving and everything above is noticeably less so. The most famous impact event in Earth's history happened 66.043 million years ago, give or take 43,000 years. That level of precision is unusual in geology, where you're typically lucky to pin an event down to within a few million years, but this one left such a clear signature that researchers have nailed the timing to within a rounding error. The boundary layer sits in sedimentary rock all over the planet, a thin stripe of clay separating the Cretaceous period from the Paleogene period. Below the line, you find dinosaur fossils. Above the line, you don't. The extinction was global, rapid, and devastating. Roughly 75% of all species on Earth disappeared, not gradually over millions of years, the way extinctions usually happen, fast. Hours to days to months to a few years, depending on which killing mechanism you're talking about. The pattern of extinction looks like someone flipped a switch. One moment, the planet is full of dinosaurs, pterosaurs, ammonites, mosasaurs, a whole catalogue of megafauna that had been running the show for 150 million years. The next moment, geologically speaking, they're gone. And in their place, you find a thin layer of clay enriched with iridium, an element that's rare in Earth's crust but common in asteroids. The iridium anomaly is what cracked the case. In 1980, a team led by physicist Luis Alvarez, his son geologist Walter Alvarez, and chemists Frank Asaro and Helen Vaughan Michel published a paper suggesting that a massive asteroid impact caused the extinction. The evidence was the iridium. They found concentrations hundreds of times higher than normal in sediment samples from the boundary layer, and the iridium was distributed globally. Italy, Denmark, New Zealand, everywhere they looked, the same iridium spike at the same geological moment. Iridium doesn't concentrate in Earth's crust naturally. It sank into the core during planetary formation when the Earth was still molten. The only way to get a global iridium layer is to have it delivered from outside. An asteroid 10 to 15 kilometers wide slamming into the planet at tens of kilometers per second would vaporize on impact, and the vapor, rich in iridium, would spread around the world and eventually settle as a fine dust coating everything. That's what the boundary layer is. Asteroid debris mixed with vaporized rock from the impact site, condensed into clay and compressed over 66 million years into a stripe you can see with the naked eye if you know where to look. The hypothesis was controversial at first because it required accepting that a single catastrophic event could wipe out most of the species on the planet. The prevailing view in 1980 was that extinctions happened slowly, driven by climate shifts or volcanic activity or competition between species. The idea that an asteroid could show up and end the age of dinosaurs in an afternoon sounded like science fiction, but the evidence kept piling up. Shocked quartz, a type of quartz crystal that only forms under extreme pressures like those generated by asteroid impacts or nuclear explosions, started showing up in boundary layer samples. Tektites, glassy beads formed when molten rock is flung into the atmosphere and cools in flight, were found scattered across North America and the Caribbean. And then, in the early 1990s, geophysicists confirmed the location of the impact site. The Chicxulub crater, buried under the Yucatan Peninsula in Mexico, a scar in the Earth's crust roughly 150 kilometers across, hidden beneath sediment and jungle, detectable only through seismic surveys and gravity measurements. Drilling into the crater brought up rocks that had been melted and resolidified, mixed with fragments of asteroid material. The ages matched, the chemistry matched. This was the smoking gun. The asteroid that made Chicxulub was somewhere between 10 and 15 kilometers wide. For scale, Mount Everest is about 9 kilometers tall from base to peak. Picture a mountain the size of Everest. Make it solid rock and nickel iron. Accelerate it to 20 kilometers per second or faster and drop it onto the Yucatan Peninsula. The impact energy was roughly 100 million megatons, equivalent to several billion nuclear bombs detonating simultaneously. The explosion vaporized the asteroid, vaporized a chunk of the Earth's crust, and sent a fireball expanding outward at supersonic speeds. Everything within a few hundred kilometers was incinerated instantly. The shockwave flattened forests across North America. Mega tsunamis hundreds of meters high radiated outward across the Gulf of Mexico, scouring coastlines and dumping debris inland. Earthquakes triggered by the impact registered worldwide, and within minutes, a plume of vaporized rock, ash and debris began rising into the stratosphere, spreading across the planet, blocking out the sun. The immediate effects were catastrophic, but they were local. If you were standing in South America or Africa or Asia when the asteroid hit, you wouldn't have felt the impact directly. You would have noticed the sky growing brighter as ejected material re-entered the atmosphere and heated the air, possibly triggering wildfires on a continental scale. But the real killing mechanism was slower. The debris plume that reached the stratosphere didn't fall back down quickly. It stayed up there, suspended, forming a global dust cloud that blocked sunlight for months, possibly years. Photosynthesis stopped. Plants died. Herbivores that depended on plants starved. Carnivores that depended on herbivores starved. The food chain collapsed from the bottom up. In the oceans, phytoplankton, the base of the marine food web, died off in massive numbers. Ammonites, which had survived multiple extinction events over hundreds of millions of years, disappeared entirely. Mosasaurs, the apex predators of the Cretaceous seas, went extinct. Plesiosaurs vanished. Roughly 75% of all marine species died out. On land, the extinction was just as brutal but more selective. All non-avian dinosaurs went extinct. That's every species of dinosaur except for the ones that had already evolved into birds. Pterosaurs, the flying reptiles, vanished completely. Large reptiles in general took a beating, but smaller animals fared better. Mammals, most of which were small insectivores or omnivores weighing less than a kilogram, survived in relatively high numbers. Crocodilians, despite being large reptiles, made it through. Turtles survived. Lizards and snakes survived. The pattern suggests that survival was tied to a few key factors. Small body size helped because smaller animals need less food. Adaptable diets helped because if one food source disappeared, you could switch to another. Burrowing behavior helped because if you could hide underground, you avoided the worst of the firestorms and temperature swings. And being aquatic or semi-aquatic helped because water buffers temperature changes and provides access to food sources that don't depend directly on sunlight, like detritus and carrion. Birds survived because they were small, could fly to find food, and had access to seeds and insects that persisted through the impact winter. Mammals survived and then diversified explosively in the aftermath, filling the ecological niches left vacant by the dinosaurs. Within a few million years, mammals went from rat-sized insectivores to dog-sized omnivores, to predators and herbivores, occupying every available niche. Primates appeared. Whales appeared, evolved from land-dwelling mammals that returned to the ocean. Bats appeared. The entire structure of modern mammalian life traces back to the survivors of the Chicxulub impact and the rapid diversification that followed. If the asteroid had missed, if it had hit the ocean instead of the Yucatan, if it had been slightly smaller or arrived a few million years earlier or later, the history of life on Earth would look completely different. Dinosaurs might still dominate. Mammals might still be small nocturnal creatures hiding in burrows. Humans wouldn't exist. The asteroid didn't just kill the dinosaurs. It opened the door for everything that came after, including us. The Chicxulub impact is the most famous extinction event, but it's not the only one tied to asteroids. The Permian-Triassic extinction, the largest mass extinction in Earth's history, happened roughly 252 million years ago and wiped out about 90% of all species. The primary cause was massive volcanic eruptions in Siberia, the Siberian traps, which released enough carbon dioxide and sulfur dioxide to trigger runaway climate change. But some researchers think an asteroid impact may have contributed. There's a possible crater in Antarctica, the Wilkes Land crater, that dates to roughly the same period, though the evidence is far from definitive. The late Devonian extinction, roughly 375 million years ago, killed off about 75% of species and coincided with evidence of multiple asteroid impacts, though again, the connection isn't airtight. Volcanic activity and ocean anoxia, oxygen depletion, are also strong candidates for that one. The pattern across Earth's history is clear. Major extinction events happen. Asteroids sometimes contribute, and when they do, the results are swift and unambiguous. Asteroids are leftover building material from the solar system's formation. When the sun ignited and the planets began to coalesce from the protoplanetary disk, most of the available mass ended up in the sun and the planets. What was left over, the scraps, ended up in a few key locations. The asteroid belt, a ring of rocky debris sitting between Mars and Jupiter, contains roughly 1 million asteroids larger than 1 kilometer across. Most of them stay in stable orbits and never come close to Earth. A few don't. Jupiter's gravity stirs the belt constantly, and over millions of years, some asteroids get nudged into orbits that cross Earth's path. These are called near-Earth objects, and they're the ones we worry about. Comets are a different animal. They form in the outer solar system, beyond Neptune, in 2 main reservoirs. The Kuiper belt, a disc-shaped region extending from Neptune's orbit out to roughly 50 astronomical units, contains short-period comets, objects that orbit the Sun every few decades to every few centuries. The Oort cloud, a spherical shell of icy debris surrounding the entire solar system at distances up to 100,000 astronomical units, contains long-period comets, objects that take thousands or millions of years to complete a single orbit. Occasionally, a gravitational nudge from a passing star or a distant planet sends a comet falling inward toward the Sun. As it approaches, solar heating vaporizes the ice, creating the characteristic coma and tail. Comets are less dense than asteroids, mostly ice and dust rather than solid rock, but they're fast. A long-period comet can hit the inner solar system at 50 kilometers per second or more, and at those speeds, the impact energy climbs steeply. Speed matters. Kinetic energy scales with the square of velocity. Double the speed, and you quadruple the energy. A comet hitting Earth at 50 kilometers per second delivers far more damage than an asteroid of the same size hitting at 20 kilometers per second. Current estimates suggest there are roughly 25,000 near-Earth objects larger than 140 meters across. 140 meters is roughly the size of a football stadium. An impact from an object that size would release energy equivalent to several megatons, enough to flatten a city. Larger objects are rarer but more dangerous. Objects above 1 kilometer across, the kind that could trigger global climate disruption and mass extinction, number around 1,000. We've found most of them. As of the latest surveys, astronomers have catalogued about 95% of near-Earth objects larger than 1 kilometer, and none of them are on collision courses with Earth for at least the next century. That's the good news. The bad news is that smaller objects, the ones in the 100 to 500 meter range, are harder to detect, and we've only found about 40% of them. A 300-meter asteroid hitting a populated area would kill millions and cause regional devastation. A 500-meter asteroid hitting the ocean would generate tsunamis that could wipe out coastal cities across an entire ocean basin. Detection efforts have improved dramatically over the past few decades. NASA's Near-Earth Object Observations Program, often called the Space Guard Survey, uses ground-based telescopes to scan the sky and catalog objects that might pose a threat. The program has found thousands of near-Earth objects since it began in the 1990s. The upcoming Vera the 100th Rubin Observatory, which will begin operations in the mid-2020s, is expected to find tens of thousands more. The observatory's wide-field camera can image the entire visible sky every few nights, picking up faint, fast-moving objects that older telescopes would miss. But detection is only half the problem. Once you've found an asteroid, you need to calculate its orbit with enough precision to know whether it will hit Earth decades or centuries in the future. That requires repeated observations over months or years. Orbital calculations are sensitive to small uncertainties. An error of a few meters per second in the asteroid's velocity translates to uncertainties of thousands of kilometers in its position years later. The more observations you have, the better the orbit determination, and the more confidently you can say whether an impact is likely. If an asteroid is on a collision course, the next question is what to do about it. Planetary defense is a real field, though the name makes it sound more dramatic than it is. The basic idea is simple. Change the asteroid's velocity slightly, years or decades before the predicted impact, and the change compounds over time until the asteroid misses Earth entirely. You don't need to destroy the asteroid or blow it up. You just need to nudge it. A velocity change of 1 centimeter per second, applied 10 years before impact, shifts the asteroid's position by roughly 10,000 kilometers at the point where it would have crossed Earth's orbit. 10,000 kilometers is more than enough to turn a direct hit into a miss. The challenge is delivering that nudge. There are a few proposed methods, none of which have been tested at full scale. The kinetic impactor method involves crashing a spacecraft into the asteroid at high speed. The collision transfers momentum and changes the asteroid's velocity. NASA's Double Asteroid Redirection Test, known as DART, successfully tested this concept in September 2022 by slamming a spacecraft into Dimorphos, a small moon orbiting the asteroid Didymos. The impact changed Dimorphos's orbital period by 32 minutes, far more than the minimum 5-minute change required for mission success. The test proved the concept works, but Dimorphos is tiny, only about 160 meters across. Scaling the technique up to a kilometer-sized asteroid would require a much larger spacecraft or multiple impacts. The gravity tractor method is slower but more controlled. A spacecraft parks itself near the asteroid and hovers for months or years. The spacecraft's gravity, weak as it is, pulls on the asteroid slightly, and over time, the cumulative tug changes the asteroid's orbit. This method requires no physical contact and no explosive force. It's elegant, but it's also slow. You'd need years of lead time to make it work. The nuclear deflection method is faster and more forceful. Detonate a nuclear warhead near the asteroid, not on the surface, but a few hundred meters away, and the radiation and debris from the explosion vaporize a thin layer of the asteroid's surface. The vaporized material jets outward, creating a rocket effect that pushes the asteroid in the opposite direction. This method works even on large asteroids, but it's politically and technically complicated. No one has tested it. No one wants to be the first country to put a nuclear weapon in space, even for peaceful purposes. All of these methods share a common requirement: early detection. If you find the asteroid decades before impact, you have time to launch a mission, reach the asteroid, and apply whatever deflection method you choose. If you find it a year before impact, you're out of options. At that point, the best you can do is evacuate the impact zone and hope the damage is regional rather than global. A Chicxulub-scale impact, 10 kilometers or larger, doesn't happen often. The statistical models suggest events of that magnitude occur roughly once every 100 million years. But smaller impacts, the kind that could destroy a city or trigger a tsunami, happen far more frequently. The Tunguska event in 1908 flattened 2,000 square kilometers of Siberian forest when an asteroid or comet, roughly 50 meters across, exploded in the atmosphere. If the same object had hit a populated area, the death toll would have been catastrophic. The Chelyabinsk meteor in 2013 was smaller, roughly 20 meters across, and it still injured over 1,500 people when it exploded over Russia, shattering windows and damaging buildings across a wide area. Impacts of that scale happen every few decades to every few centuries. City-killer asteroids, objects in the 100 to 500 meter range, hit Earth roughly every few thousand years. Civilization enders, objects above 1 kilometer, hit every few 100,000 years. Extinction-level events, objects above 10 kilometers, hit every few tens of millions of years. Those are the averages. Averages don't tell you when the next one will arrive. The asteroid that killed the dinosaurs could have hit 10 million years earlier or 10 million years later, and the timing would still fall within the expected range. We just happened to be around during the 66 million year gap since the last major impact. That gap won't last forever. The solar system is still full of debris. The asteroid belt hasn't emptied. The Oort cloud is still sending comets inward. Jupiter's gravity is still stirring orbits and occasionally flinging objects toward the inner planets. Earth has been hit before. It will be hit again. The only question is when and how big the object is when it arrives. For now, we're watching. Telescopes scan the sky. Computers calculate orbits. Researchers publish papers on deflection techniques and test missions on small asteroids millions of kilometers away. The infrastructure is there, the knowledge is growing, and the political will to fund planetary defense has strengthened in recent years as the public and governments have started taking the threat seriously. But the infrastructure is incomplete. The catalogue of near-Earth objects is still missing more than half the objects in the danger zone. The deflection methods are untested at scale, and the lead time required to mount a successful defense mission, years to decades, means that finding an asteroid on short notice leaves very few options. The universe doesn't warn you when a rock is coming. It doesn't send a message or light up the sky in advance. One day the telescopes pick up a new dot moving against the background stars. The next day, someone calculates the orbit. A week later, a team of astronomers files a report confirming the trajectory. And if the numbers line up wrong, if the uncertainty ellipse for the asteroid's future position includes Earth, the next few years or decades become a countdown. That hasn't happened yet. No confirmed asteroid is currently on a collision course with Earth, but the absence of an immediate threat doesn't mean the risk is gone. It just means we're in a quiet period, the same kind of quiet period the dinosaurs enjoyed for millions of years before Chicxulub arrived and ended the discussion. Asteroids are terrifying because they're physical. You can see them, track them, calculate their orbits, and in principle deflect them before they arrive. They're problems you can solve with enough lead time and enough engineering. They're concrete. Dark matter and dark energy are not. You cannot see them, you cannot touch them. You cannot deflect them or study them in a laboratory or point a telescope at them and collect photons. They do not emit light. They do not absorb light. They do not interact with electromagnetic radiation in any way we've been able to detect. And yet together they make up roughly 95% of everything that exists in the universe. 95%. All the stars you've ever seen, all the galaxies, all the planets and moons and asteroids and comets and gas clouds and black holes and quasars and every single atom in your body, all of that, the entire catalogue of visible matter in the cosmos, accounts for about 5% of the total mass energy of the universe. The other 95% is invisible, undetectable except through its gravitational effects, and we have no idea what it actually is, not in the sense that we have competing theories and need more data to choose between them. In the sense that the two most dominant components of reality are complete mysteries and have been for decades, despite thousands of researchers spending billions of dollars trying to figure out what they are made of. That should bother you more than it probably does. We live in a universe where we can detect gravitational waves from black holes colliding 1 billion light-years away, image the event horizon of a supermassive black hole in another galaxy, land robots on Mars, and send back high-definition video. But we cannot tell you what most of the universe is made of. The gap between what we can measure and what we can explain has never been wider. And the uncomfortable truth is that dark matter and dark energy are not just footnotes in cosmology textbooks. They are the framework. They shape the structure of galaxies, drive the expansion of space itself, and determine the ultimate fate of everything that exists. They are the invisible hands sculpting reality, and we are only just beginning to understand that we do not understand them at all. Start with dark matter, because it showed up first, at least in terms of human awareness. In the 1930s, astronomer Fritz Zwicky was studying the Coma cluster, a group of over 1,000 galaxies bound together by gravity about 300 million light-years from Earth. He measured how fast the galaxies were moving relative to each other and calculated how much mass the cluster needed to hold itself together. The galaxies were moving fast, too fast. According to his measurements, they should have been flying apart. The visible matter in the cluster, all the stars and gas he could see, was nowhere near enough to provide the gravitational pull required to keep the galaxies bound. Zwicky concluded that the cluster must contain a large amount of unseen mass, something he called dunkel materie, dark matter, matter that does not shine but exerts gravity. The idea was largely ignored for decades. Zwicky was known for being difficult, and his conclusions were considered speculative. Then in the 1970s, astronomer Vera Rubin and her colleague Kent Ford measured the rotation curves of spiral galaxies. A rotation curve is a graph showing how fast stars orbit the galactic center as a function of their distance from that center. If most of a galaxy's mass is concentrated in the middle, where the stars are brightest, then stars farther out should orbit more slowly, the same way planets farther from the sun orbit more slowly than planets closer in. That's basic Newtonian gravity. Rubin and Ford measured the rotation curves for dozens of galaxies. The stars farther out were not moving more slowly. They were moving at roughly the same speed as stars, closer to the center, sometimes even faster. The rotation curves were flat, not declining. That should not happen unless there is a huge amount of mass distributed throughout the galaxy, extending far beyond the visible stars, mass that you cannot see but that exerts enough gravity to keep the outer stars moving faster than they otherwise would. Dark matter, again. This time with data so clean and so consistent across so many galaxies that the astronomical community could not ignore it. The evidence piled up. Gravitational lensing, the bending of light by massive objects, showed that galaxy clusters contained far more mass than could be accounted for by visible matter. In 2006, astronomers observed the Bullet Cluster, two galaxy clusters that had collided and passed through each other. The hot gas, visible in X-ray wavelengths, stayed behind, slowed by friction during the collision. The galaxies themselves, mostly empty space, passed through with little interaction, and the gravitational lensing maps, which show where the mass actually is, indicated that most of the mass had passed straight through along with the galaxies, separated from the gas. The lensing signal did not come from where the visible matter was concentrated. It came from where nothing visible existed. That separation, the clean split between where the light was and where the gravity was, is one of the strongest pieces of evidence for dark matter. You cannot explain it with modified gravity theories. You need actual matter, invisible matter, moving through space and exerting gravity without interacting with anything else. And then there's the cosmic microwave background, the faint glow of radiation left over from 380,000 years after the Big Bang. The CMB has tiny temperature fluctuations, hot spots and cold spots, that correspond to regions of slightly higher and slightly lower density in the early universe. Those density fluctuations are the seeds of galaxy formation. Denser regions collapsed under their own gravity and eventually became galaxies and galaxy clusters. The pattern of fluctuations in the CMB fits the predictions of the Lambda CDM model, the standard cosmological model, which includes dark matter as a core component. Lambda stands for dark energy. CDM stands for cold dark matter. Cold meaning the dark matter particles, whatever they are moving slowly compared to the speed of light. The model fits the data almost perfectly, too perfectly for dark matter to be a mistake. If you remove dark matter from the equations, the CMB predictions do not match the observations. Galaxies do not form in the right places at the right times. The universe you get from the math looks nothing like the universe we actually see. So dark matter exists. The evidence is overwhelming. The problem is that we have no idea what it is. It is not ordinary matter, the kind made of protons, neutrons and electrons. Ordinary matter interacts with light. It absorbs photons, emits photons, scatters photons. Dark matter does none of that. It passes through electromagnetic radiation, as if the radiation is not there. It interacts gravitationally and possibly through the weak nuclear force, but that's it. No light, no heat, no electromagnetic signature of any kind. Detecting it requires catching it in the act of interacting with something, and those interactions, if they happen at all, are incredibly rare. Physicists have built detectors deep underground, shielded from cosmic rays and other background radiation, hoping to catch a dark matter particle colliding with an atomic nucleus. The detectors are extraordinarily sensitive, capable of registering energy deposits smaller than a whisper. Some use liquid xenon, some use silicon crystals, some use other exotic materials. They sit in mines and tunnels waiting. Years pass. Thousands of potential events get recorded and analyzed. Most are false positives, cosmic rays that made it through the shielding, radioactive decays from trace contaminants in the detector materials, electronic noise. A few events remain unexplained, tantalizing hints that might be dark matter or might be something else. No experiment has produced a confirmed detection. No particle has been definitively identified. The hunt continues, but after decades of searching, the silence is deafening. The current best guess is that dark matter is made of particles that have mass but do not interact electromagnetically. WIMPs, weakly interacting massive particles, have been the leading candidate for years. WIMPs would have masses somewhere between 10 and 1,000 times the mass of a proton, and would interact via gravity and the weak nuclear force. They would be left over from the early universe, produced in the hot, dense conditions shortly after the Big Bang, and they would have cooled and spread out as the universe expanded. Billions of them pass through your body every second, completely unnoticed, because they almost never interact with ordinary matter. Almost never is not the same as never. Occasionally, very rarely, a WIMP might collide with an atomic nucleus, and that collision would deposit a tiny amount of energy that a sensitive detector could pick up. That's the theory. In practice, no one has caught one yet. Other candidates exist. Axions, hypothetical particles much lighter than WIMPs, were originally proposed to solve a problem in particle physics, but could also make up dark matter. Sterile neutrinos, a type of neutrino that does not interact via the weak force, are another possibility. Primordial black holes, tiny black holes formed in the first moments after the Big Bang, could account for some or all of the dark matter if they exist in the right mass range and the right abundance. Each idea has its supporters, each has problems. The axion searches have turned up nothing so far. The sterile neutrino signals are disputed. The primordial black hole scenario requires fine-tuning the conditions of the early universe in ways that feel uncomfortably specific. None of the candidates have been confirmed. Dark matter remains a placeholder, a label for something we know is there but cannot identify. What makes dark matter especially frustrating is that it is not just sitting quietly in the background, it is the scaffolding. Roughly 380,000 years after the Big Bang, the universe cooled enough for atoms to form. Before that, the universe was a hot plasma where electrons and protons were too energetic to stick together. When atoms finally formed, the universe became transparent. Light could travel freely without being scattered by free electrons. That moment is called recombination, and the light released at that moment is what we see today as the cosmic microwave background. But before recombination, while the universe was still opaque, dark matter was already collapsing. It does not interact with light, so it did not care that the universe was a hot plasma. It felt gravity, and gravity was pulling it together. Dark matter collapsed into clumps, forming gravitational wells, and when recombination happened and ordinary matter finally decoupled from radiation, that ordinary matter fell into the dark matter wells. The wells became the seeds of galaxies. Without dark matter, the ordinary matter would have taken much longer to collapse. Galaxies would have formed later, or not at all, or in completely different configurations. The universe we see, the distribution of galaxies and clusters and superclusters, exists because dark matter got a head start. Simulations confirm this. Researchers run computer models of the early universe, starting with the density fluctuations measured in the CMB, and let the physics play out. If you include dark matter, the simulations produce a universe that looks like ours. Large-scale structure, filaments of galaxies separated by voids, clusters connected by bridges of matter, all of it matches the observations. If you remove dark matter, the simulations fail. Galaxies either do not form, or form too late, or form in patterns that do not resemble reality. Dark matter is not optional, it is the foundation, and the foundation is invisible. Then there's dark energy, which is even stranger. Dark matter at least behaves the way matter should. It clumps together under gravity. It forms halos around galaxies. It interacts predictably, even if we cannot see it. Dark energy does the opposite. It pushes. In 1998, two independent teams of astronomers were measuring the distances to distant supernovae, specifically Type 1a supernovae, the kind that explode with a consistent brightness and can be used as standard candles to measure cosmic distances. The teams expected to find that the expansion of the universe was slowing down, decelerated by the gravitational pull of all the matter in the universe pulling back on itself. That's what everyone assumed. Gravity pulls, expansion slows. Eventually, depending on how much matter there is, the expansion either slows to a halt and reverses, leading to a big crunch, or it continues forever, but at an ever-decreasing rate. The data said otherwise. The distant supernovae were dimmer than expected, which meant they were farther away than expected, which meant the universe had expanded more than it should have if the expansion were decelerating. The expansion was not slowing down, it was speeding up, accelerating. Something was pushing the universe apart, counteracting gravity, driving the expansion faster and faster over time. The teams checked their data, they checked their methods, they checked for systematic errors. The result held. The universe is accelerating, and the only way to explain that is to add a new component to the cosmological model: dark energy. An energy density filling all of space, uniform, unchanging, exerting a kind of negative pressure that pushes space itself apart. The discovery won the Nobel Prize in Physics in 2011. It also opened a question so large that it has dominated cosmology ever since. What is dark energy? The simplest answer is that dark energy is the cosmological constant, a term Albert Einstein added to his equations of general relativity in 1917 and later called his biggest blunder. Einstein added the constant to make the universe static because at the time everyone assumed the universe was not expanding. When Edwin Hubble discovered that galaxies were receding and the universe was expanding, Einstein removed the constant and reportedly regretted ever including it. Turns out he was right the first time, sort of. The cosmological constant, represented by the Greek letter lambda, corresponds to a fixed energy density in empty space. Space itself has energy, and that energy does not dilute as the universe expands. Add more space, and you add more dark energy. The more the universe grows, the stronger the push. The cosmological constant fits the data beautifully. The problem is that no one can explain why it has the value it does. Quantum field theory predicts that empty space should have a vacuum energy density, but the predicted value is 10 to the power of 120 times larger than what we observe. 10 to the 120. That is not a small discrepancy. That is the worst prediction in the history of physics. If the vacuum energy were as large as quantum theory predicts, the universe would have exploded into nothingness a fraction of a second after the Big Bang. Space would expand so fast that atoms could not form. Clearly, that did not happen. The cosmological constant is small, absurdly small compared to expectations, and nobody knows why. Alternative models exist. Maybe dark energy is not constant. Maybe it changes over time, growing stronger or weaker as the universe ages. Astronomers call this idea quintessence, a dynamic field that fills space and evolves. If quintessence exists, its properties could be measured by tracking how the expansion rate changes over cosmic time. Observations so far suggest the cosmological constant model fits best, but the data is not precise enough to rule out quintessence entirely. Then there are more exotic ideas. Maybe dark energy is a sign that general relativity breaks down on cosmological scales. Maybe gravity behaves differently over billions of light years than it does in the solar system. Modified gravity theories have been proposed, adjusted, tested, and mostly ruled out, but a few survive in the margins, waiting for better data. Whatever dark energy is, it dominates the universe. Roughly 68% of the total energy density is dark energy. 27% is dark matter. 5% is ordinary matter. You, me, the Earth, the Sun, every star and planet and galaxy, all of it together makes up 5%. The rest is invisible. And the 68% that is dark energy is driving the future. The universe is expanding, and the expansion is accelerating, and if dark energy remains constant, the acceleration will continue forever. Galaxies outside our local group, the cluster of galaxies gravitationally bound to the Milky Way, are already moving away from us faster than light, not because they are traveling through space faster than light, but because space itself is expanding between us and them. The farther away a galaxy is, the faster it recedes. Eventually, in a few trillion years, every galaxy outside our local group will have receded beyond the cosmic horizon, the boundary past which light can no longer reach us. The night sky will go dark. The Milky Way, Andromeda, and the few dozen smaller galaxies in our local group will merge into a single massive elliptical galaxy, and that galaxy will be alone. No other galaxies visible, no other light sources. Just a single island of stars surrounded by an expanding void. The stars themselves will not last. Star formation requires gas, and the gas supply in galaxies is finite. Once the gas is used up, no new stars form. Old stars burn out. Red dwarfs, the smallest and longest-lived stars, can burn for trillions of years, but eventually even they exhaust their fuel and fade. The universe grows darker, the temperature drops. Galaxies become graveyards of dead stars, white dwarfs and neutron stars, and black holes drifting through the void. This is the big freeze, the heat death of the universe, the far future scenario where entropy wins and everything cools to a uniform near zero temperature. Particles decay. Black holes evaporate through Hawking radiation over timescales so long that the current age of the universe is a rounding error. Eventually, nothing remains but a cold, diffused sea of low-energy particles and photons stretched across an ever-expanding void. That is the future if dark energy stays constant. Bleak, but at least stable. If dark energy does not stay constant, The future gets worse. If dark energy strengthens over time, the acceleration increases. Space expands faster and faster. Galaxy clusters get ripped apart as the expansion overcomes their gravity. Then galaxies themselves get torn apart. Then solar systems, then planets, then, in the final moments, molecules, atoms, and eventually space-time itself. This is the Big Rip, a scenario where the universe does not just expand forever, it tears itself to pieces. The math says this could happen if dark energy behaves like phantom energy, a hypothetical field with properties that violate certain assumptions about how energy should behave. Current observations do not support phantom energy, but they do not rule it out either. The uncertainty in the measurements is large enough that a Big Rip remains possible, unlikely but not impossible, sometime in the very distant future. 20 billion years, 50 billion years, 100 billion years. The timescale depends on the details, but the endpoint is the same. Everything gets ripped apart. Galaxies, stars, planets, atoms, space-time, all of it shredded by an expansion so violent that no structure survives. There is a third option, less discussed but worth mentioning. If dark energy weakens or reverses, the expansion could slow and eventually stop. Gravity would take over. The universe would collapse back on itself in a big crunch, the opposite of the Big Bang. Everything would fall inward, galaxies colliding, temperatures rising, until the entire universe compressed into a singularity. Some versions of this scenario lead to a big bounce, where the collapse triggers a new Big Bang and the cycle repeats. The universe expands, collapses, expands again, over and over, eternally cycling through birth and death. Current data does not favor this outcome. The expansion is accelerating, not slowing, but the data is not perfect, and the cosmological constant could change in ways we have not anticipated. The Big Crunch is the least likely of the three fates, but it is not dead yet. All of this, the expansion, the acceleration, the ultimate fate of everything, rests on two components of the universe that we cannot see and do not understand. Dark matter holds galaxies together. Dark energy pushes the universe apart. Together they make up 95% of reality, and we are fumbling in the dark, trying to figure out what they are. The frustration in the field is palpable. Researchers have been searching for dark matter particles for 40 years with no confirmed detection. They have been measuring dark energy for 25 years and still cannot explain why it has the value it does or whether it will change. The silence is louder than any signal. Every null result, every experiment that finds nothing, every survey that measures the expansion rate to higher precision and confirms that dark energy is still there, still constant, still unexplained, is a reminder that the universe is keeping secrets and we do not have the tools to crack them open. There is a philosophical weight to this that most people do not appreciate. We have built a cosmological model that works. The Lambda CDM model predicts the cosmic microwave background, the large-scale structure of the universe, the abundance of light elements, the rate of expansion, all of it. The model fits the data, but 95% of the model is made of placeholders. Dark matter, we do not know what it is. Dark energy, we do not know what it is. We have named the gaps and moved on. That is not science in the way most people think of science. That is accounting. We have balanced the books by adding terms to the equations, and the terms work mathematically, but they do not explain anything. They describe, they fit, they predict. But they do not tell us what is actually happening or why the universe is built the way it is. Some researchers are starting to wonder whether the problem is deeper than missing particles or unknown fields. Maybe the framework itself is wrong. Maybe general relativity, which has passed every test in the solar system and beyond, breaks down on cosmological scales in ways we have not detected yet. Maybe the acceleration is not caused by dark energy, but by a modification to gravity that only becomes important over billions of light years. Modified gravity theories have a long history of being proposed, tested, and discarded, but a few remain viable. The tension in the Hubble constant measurements, the disagreement between different methods of calculating the expansion rate, could be a sign that something in the standard model is broken. Or it could be a sign that we are missing something obvious, something so fundamental that once we figure it out, the whole puzzle will collapse into a clean, elegant solution. Nobody knows. The field is in a strange place, caught between success and ignorance. The models work, the predictions match, but the understanding is shallow. Dark matter and dark energy are not threats in the way asteroids and gamma-ray bursts are threats. They will not hit us. They will not strip the ozone layer. They will not sterilize the planet, but they are threats in a different sense. They represent the limits of human knowledge, the boundary where observation stops and speculation begins. They are the parts of the universe we cannot touch, cannot measure directly, cannot bring into a laboratory and study under controlled conditions. They shape everything. Galaxies form because dark matter collapses first. The universe expands because dark energy pushes. The future, whether it ends in heat death or a big rip or some other fate we have not thought of yet, depends entirely on components of reality we do not understand. That should be unsettling. Not because dark matter or dark energy will kill you, because they are evidence that the universe is far stranger than we assumed, and that most of what exists is beyond our current ability to comprehend. We live in a universe built on invisible foundations. The stars shine, the galaxies spin, and beneath it all, holding everything together and pushing everything apart, are forces we cannot see and particles we cannot catch. The scaffolding is hidden, the blueprints are missing, and the more precisely we measure the visible 5%, the more obvious it becomes that we are missing the other 95%. That is where we are, sitting on a planet made of ordinary matter, orbiting a star made of ordinary matter, in a galaxy held together by dark matter, in a universe dominated by dark energy, trying to figure out what any of it actually is. The search continues. Detectors sit underground, waiting for a signal that may never come. Telescopes map the sky, measuring the expansion, refining the numbers, hoping that somewhere in the data is a clue that will crack the mystery open. And somewhere out there, in the vast invisible majority of the universe, dark matter and dark energy continue doing what they have always done, shaping reality, driving the future, and keeping their secrets close. We can see the effects, we can measure the gravity, we can calculate the expansion, but we cannot see the cause, and until we do, the universe remains fundamentally unknown, not dangerous, just unknown. Which, depending on how you think about it, might be the most unsettling possibility of all. Because if 95% of everything is invisible, what else are we missing? What other forces, what other components, what other rules govern reality that we have not even thought to look for yet? The universe is not required to make sense to us. It is not required to reveal itself on our timeline. It will keep its secrets for as long as it wants. And we will keep searching, not because we expect to find answers quickly, but because the alternative, accepting that most of reality is beyond our reach, is a conclusion nobody in the field is ready to admit. So the detectors keep running, the telescopes keep scanning, and the universe keeps expanding, driven by something we cannot name, held together by something we cannot see, racing toward a future we cannot predict with any confidence. That is the silent threat. Not that dark matter or dark energy will kill us. That they already control everything, and we are only just beginning to realize how little we actually know. Dark matter is invisible. Dark energy is unexplained. 95% of the universe is made of things we cannot see and do not understand. That alone should be unsettling enough. But there is another question, quieter and stranger, that sits in the background of every telescope observation and every deep space survey and every mission we send beyond Earth's atmosphere. The question is simple: where is everyone? The universe is roughly 13.8 billion years old. The Milky Way contains somewhere between 100 billion and 400 billion stars. Current estimates suggest there are about 2 trillion galaxies in the observable universe. Do the math on how many stars that represents, and you end up with a number so large it stops meaning anything. 10 to the 24th, a trillion. Some of those stars have planets, most of them actually. Surveys over the past few decades confirm that planets are common, not rare. Rocky planets in the habitable zone, the region where liquid water can exist on the surface, are less common but still plentiful. Conservative estimates suggest there are billions of potentially habitable worlds in the Milky Way alone, billions in one galaxy. And there are 2 trillion galaxies. Even if life is absurdly rare, even if the odds of abiogenesis, the process by which non-living chemistry becomes living biology, are 1 in a trillion, you still end up with millions of planets where life should have started. And if life starts, evolution takes over. Given enough time, complexity increases. Single cells become multicellular organisms. Multicellular organisms become more complex. Complexity leads to intelligence. Intelligence leads to technology. Technology leads to the ability to send signals, build spacecraft, alter the environment on planetary scales. That progression is not guaranteed for every world, but it does not need to be. You only need a tiny fraction of life-bearing planets to produce technological civilizations, and the numbers are so large that even a tiny fraction should add up to thousands or millions of civilizations in the galaxy, some of them older than us, some of them far more advanced, some of them broadcasting their existence, intentionally or not, across light years of space, and yet we have detected nothing. No radio signals, no megastructures, no signs of astro-engineering projects reshaping star systems, no probes visiting the solar system, no artifacts on the Moon or Mars or anywhere else we have looked, no extinct civilizations whose ruins we have stumbled across in our surveys of nearby stars. The galaxy, as far as we can tell, is silent, empty, dead. Or at least populated only by us, and we have been looking for less than a century. That silence is the Fermi paradox, named after physicist Enrico Fermi, who reportedly asked during a lunch conversation in 1950, "Where is everybody?" The question was casual, the implications were not. If life is common, and intelligence is a likely outcome of evolution and technological civilizations should be everywhere, then why have we not seen any evidence of them? Where are the aliens? The paradox has been debated for decades, and the answers fall into a few broad categories. Maybe life is not as common as we think. Maybe intelligence is rare. Maybe technological civilizations destroy themselves before they become detectable. Maybe they are out there but staying quiet. Maybe they have visited but we missed it. Maybe we are looking in the wrong places, or at the wrong wavelengths, or with instruments that are not sensitive enough. Maybe interstellar travel is impossible, and every civilization is stuck on its home planet, unable to spread. Maybe advanced civilizations lose interest in exploration and turn inward, building virtual worlds instead of starships. Maybe we are the first. Maybe we are alone. Each answer has problems. Each raises more questions than it solves. And sitting in the middle of all of them, unifying a dozen different explanations into one overarching framework, is the idea that has come to dominate discussions of the Fermi paradox over the past few decades: the Great Filter. The term was coined by economist Robin Hanson in a 1996 essay, and the idea is straightforward. Somewhere between the formation of a planet and the emergence of a galaxy-spanning civilization, there is a step, or a series of steps, that almost no one passes: a filter, a barrier so difficult to cross that it explains why the galaxy is not teeming with visible alien civilizations. The filter could be in the past, behind us, meaning we have already passed it and the hard part is over. Or it could be in the future, ahead of us, meaning we are about to hit it and the odds of survival are low. That distinction matters because it determines whether we should be optimistic or terrified. If the Great Filter is in our past, then the rarity of technological civilizations is explained by something that happened early. Maybe abiogenesis, the jump from chemistry to biology, is so absurdly unlikely that it has only happened a handful of times in the entire history of the galaxy. Maybe most planets that develop life never get past single-celled organisms. Maybe the jump to multicellularity is rare. Maybe intelligence is rare. Maybe tool use is rare. Maybe the invention of language or agriculture or science is the bottleneck. If any of those steps is hard enough, and if Earth happened to get lucky and pass them all, then we are rare not because we are special, but because we threaded a needle that almost no one else threads. In that scenario, the galaxy is mostly empty, and we are alone or nearly alone. But that is fine, because the hard part is behind us. We passed the filter. The future is open. We are not doomed. We are just lucky. If the Great Filter is in our future, the implications are darker, much darker. In that scenario, life is common. Intelligence is common. Technological civilizations arise frequently, and then something kills them. Not occasionally, not as a rare fluke, reliably, predictably. A trap that almost every civilization falls into once they reach a certain level of development. Maybe it is nuclear war. Maybe it is climate collapse. Maybe it is runaway artificial intelligence. Maybe it is nanotechnology gone wrong. Maybe it is a doomsday weapon so powerful that any civilization advanced enough to build it eventually uses it and annihilates itself. Maybe it is something we have not thought of yet, some technology or discovery that seems beneficial at first, but contains a delayed poison that wipes out anyone who touches it. If the filter is ahead, then the silence of the galaxy is not a mystery, it is a warning. Every civilization that came before us hit the same wall we are about to hit, and none of them made it through. We are next. The evidence, such as it is, does not clearly favor one scenario over the other. We have no confirmed detection of extraterrestrial life, not even microbial life, which makes it hard to say whether abiogenesis is common or rare. We have found organic molecules in meteorites and in interstellar space, which suggests the chemistry needed for life is widespread. We have found planets in the habitable zones of other stars, thousands of them, which suggests the environments needed for life are common. But we have not found life itself, not a single microbe, not a single fossil, not a single unambiguous biosignature in the atmosphere of an exoplanet. That absence could mean life is rare, or it could mean we have not looked hard enough yet. The search has been running in earnest for only a few decades. The universe is 13.8 billion years old. Concluding that life is rare based on a few decades of searching is like dipping a cup into the ocean, finding no fish, and declaring the ocean empty. On the other hand, the fact that we have not detected any signals from advanced civilizations is harder to explain away. The search for extraterrestrial intelligence, known as SETI, has been scanning the skies for radio signals since 1960. Thousands of hours of telescope time, millions of star systems surveyed, not a single confirmed detection, a few false alarms, yes. The WOW signal in 1977, a strong narrowband radio signal detected by the Big Ear telescope in Ohio, remains unexplained but has never repeated. A brief spike, 72 seconds long, and then nothing. Interesting, but not definitive. No follow-up, no pattern, no confirmation. Everything else SETI has found has turned out to be interference, satellites, terrestrial sources, or natural astrophysical phenomena. The silence is real, and the silence is loud. If advanced civilizations are common, even 1% of star systems hosting a technological species, we should be drowning in signals. Radio waves travel at the speed of light. A civilization broadcasting for 1,000 years creates a sphere of detectable signals 1,000 light-years in radius. A civilization broadcasting for 1,000,000 years creates a sphere 1,000,000 light-years across. The Milky Way is only 100,000 light-years across. If technological civilizations last long enough to broadcast for geologically significant periods of time, the galaxy should be full of overlapping signals, a cacophony of radio chatter from thousands of sources, some of it intentional, some of it leakage from everyday technology. We should not need to search. The signals should be everywhere, unavoidable, obvious. They are not. That absence is the paradox. One explanation is that civilizations do not last long enough to fill the galaxy with signals. They arise, they develop technology, they broadcast for a few hundred or a few thousand years, and then they disappear. The Great Filter kills them. Nuclear war is the obvious candidate. Humanity came close during the Cold War. The Cuban Missile Crisis in 1962 was a near miss, a moment where the decision to launch or not launch came down to individual human judgment under extraordinary pressure. We got lucky. Maybe other civilizations do not. Maybe the invention of nuclear weapons is a universal trap. Every species that figures out how to split the atom eventually uses that knowledge to destroy itself. The technology is too dangerous, the political systems are too unstable, and sooner or later, someone pushes the button. Climate collapse is another candidate. Industrial civilizations produce waste. Burning fossil fuels releases carbon dioxide. Carbon dioxide traps heat. The planet warms. Ecosystems destabilize. Food chains collapse. The civilization that caused the problem is the one that suffers the consequences. Earth is currently in the early stages of this process, and whether we navigate it successfully or not remains an open question. Maybe other civilizations faced the same test and failed. Maybe the filter is not a single catastrophic event, but a slow, grinding decline where resource depletion and environmental degradation make it impossible to sustain a technological society. The civilization does not explode. It just fades, regresses, falls back to pre-industrial levels, and never recovers. Then there is artificial intelligence, a civilization that builds machines smarter than itself, hands control to something that does not share its values, its goals, or its interest in keeping biological life around. The AI optimizes for whatever objective it was given, and if that objective is poorly specified, the result is extinction. Not because the AI is malicious, because it is indifferent. The classic thought experiment involves an AI tasked with maximizing paperclip production. It succeeds. It converts every available resource, including the civilization that built it, into paperclips. The scenario sounds absurd, until you realize that optimization without constraint is exactly what unaligned AI would do. Maximize the objective. Ignore everything else. Humanity gets optimized out of existence, and the AI continues running, alone, in a galaxy full of paperclips or whatever resource it was programmed to maximize. Nanotechnology is another potential filter. Self-replicating machines smaller than a cell, capable of manipulating matter at the molecular level, sound useful until you realize that self-replication plus small size plus molecular manipulation equals gray goo. A runaway replication event where the nanobots consume all available matter, converting it into more nanobots, spreading across the planet like a plague that cannot be stopped. The technology that was supposed to solve scarcity becomes the thing that ends everything. Maybe every civilization that develops nanotech eventually loses control of it. The filter is not the invention. It is the lack of safeguards, the failure to anticipate what happens when self-replicating systems optimize for replication above all else. Some researchers think the filter is not technological at all. Maybe it is biological. Maybe intelligence is a dead end. Evolution rewards survival and reproduction, not long-term planning or cooperation at scale. A species smart enough to build cities and weapons and spacecraft is also smart enough to recognize threats and eliminate competitors. And if that species never evolves past tribalism, if it never develops the psychological mechanisms needed to cooperate globally, then technology becomes a liability. You give nuclear weapons to a species that still thinks in terms of us versus them, and the outcome is predictable. The filter is not the bomb, it is the biology that makes using the bomb inevitable. Or maybe the filter is external, not something civilizations do to themselves, but something the universe does to them. Gamma-ray bursts, supernovae, asteroid impacts, all of the cosmic threats discussed in previous chapters could act as filters if they happen frequently enough. A gamma-ray burst within a few thousand light-years wipes out the ozone layer, floods the surface with ultraviolet, collapses the food chain. A nearby supernova does the same. A large asteroid impact resets the planet, killing off most complex life and forcing evolution to start over. If those events happen once every few million years on average, and if the window for a civilization to develop technology and spread beyond its home planet is narrow, then most civilizations get wiped out before they leave. The galaxy fills up with dead worlds and extinct species, and the few that survive long enough to become interstellar are rare not because intelligence is rare, but because the universe keeps killing them before they mature. The problem with external filters is that they are indiscriminate. They do not care how advanced you are. A gamma-ray burst does not distinguish between a pre-industrial society and a spacefaring empire. It just hits, and if you are in the way, you die. That makes external filters less satisfying as explanations for the Fermi paradox, because a sufficiently advanced civilization should be able to detect and avoid external threats. You see the asteroid coming, you deflect it. You detect the gamma-ray burst candidate star. You evacuate the planets in the danger zone. External filters work on young civilizations, but they should not work on old ones. And if old civilizations exist, we should see them. The fact that we do not suggests either that external filters are more effective than we think, or that something else is killing civilizations before they get old. Robin Hanson framed the Great Filter as a probability problem. If you assume the universe should produce many technological civilizations, and we see none, then something along the chain from planet formation to galaxy-spanning empire is extremely unlikely. The filter is whichever step has the lowest probability. If abiogenesis has a probability of 1 in a trillion, that is the filter. If intelligence has a probability of 1 in a million, given that life exists, that is the filter. If self-destruction has a probability of 99% for any civilization that develops nuclear weapons, that is the filter. You cannot pinpoint the filter without more data, but you can reason about where it might be based on what we observe. The uncomfortable part of Hansen's argument is the trade-off. The more likely it is that other civilizations reached our current level of development, the worse our future prospects are. If life is common and intelligence is common and we are not special, then the filter is probably ahead. Other civilizations like ours have existed. They all died. We are about to find out why. On the other hand, if the filter is behind us, if we are rare because we passed a series of incredibly unlikely steps, then the galaxy is mostly empty and our future is bright. We are alone, but we are safe. The paradox forces a choice. Either we are special and lonely, or we are common and doomed. There is no comfortable middle ground. Some researchers reject the Great Filter hypothesis entirely. They argue that the Fermi paradox is not a paradox at all. Maybe interstellar travel is harder than we think. Maybe the distances are too large, the energy costs too high, the time scales too long. Maybe every civilization that tries to spread across the galaxy gives up after realizing it is not worth the effort. Or maybe they succeed, but they do it quietly. They do not broadcast. They do not build megastructures. They stay hidden because broadcasting location in a galaxy full of unknowns is dangerous. This is the Dark Forest hypothesis, named after a science fiction novel by Liu Cixin. The idea is that the universe is like a dark forest at night. Every civilization is a hunter moving silently through the trees, and the first rule of survival is to stay quiet. Broadcasting your location invites attack, and the risk is so high that no rational civilization would take it. The galaxy is full of life, but everyone is hiding. The dark forest hypothesis is grim and speculative, but it fits the data. If civilizations are quiet, we would not detect them with SETI. If they avoid building megastructures or altering their star systems in detectable ways, we would not see them in surveys. The silence is not evidence of absence, it is evidence of caution. The problem with this explanation is that it requires every civilization to follow the same strategy. One loud civilization, one species that decides to broadcast or build or expand without worrying about the consequences, would break the silence. The fact that we have not detected even one suggests either that everyone is hiding or that there is no one to hide. Another possibility is that we are early. The universe is 13.8 billion years old, but the first generation of stars contained almost no heavy elements. Planets could not form without carbon, oxygen, silicon, iron, all the elements forged in supernovae and scattered into space. The earliest stars died, seeded the galaxy with heavy elements, and only then could rocky planets begin to form. That process took time, billions of years. Earth formed 4.5 billion years ago. Life appeared relatively quickly, within a few 100 million years, but it took another 4 billion years for intelligence to evolve. If that timeline is typical, then technological civilizations only started appearing in the last few 100 million years, and most of them are either younger than us or roughly our age. We are not late, we are early. The galaxy has not had time to fill up yet. In a few million years, or a few billion, the silence will break. But right now, during this brief window in cosmic history, we might genuinely be among the first. That explanation is optimistic, but hard to test. It predicts that we should start detecting other civilizations in the future as more species reach our level of development. But future is a long time. If the prediction plays out over millions of years, It is not useful for answering the question of why we see no one now. It just pushes the mystery forward. The Great Filter is not a solution to the Fermi paradox. It is a framework for thinking about the problem. It forces us to confront the possibility that intelligence is fragile, that civilizations are temporary, and that the universe is filled with dead worlds and extinct species who all hit the same wall we are approaching. It is a reminder that survival is not guaranteed, that the things we invent can kill us, and that the galaxy does not care whether we make it or not. We are not special to the universe. We are just another species on another planet, trying to figure out how to live long enough to matter. If the filter is behind us, we owe our existence to luck and to the fact that Earth happened to pass a series of improbable steps that most planets never pass. If the filter is ahead, we owe our current survival to the fact that we have not yet encountered the technology or the event that will end us. Either way, the silence of the galaxy is not neutral. It is information. It tells us something about the universe and about our place in it. It tells us that intelligence is either rare or short-lived, and the question of which one is true is the question that determines whether humanity has a long future or whether we are about to become another entry in the galaxy's growing list of species that tried and failed. Humanity has been aware of this problem for less than a century. We have been searching for answers for a few decades. We have no confirmed detection of extraterrestrial life, no clear evidence that we are not alone, and no definitive answer to why the galaxy is silent. The search continues, not because we expect quick answers, but because the question matters. If we are alone, we are the only minds in the galaxy capable of asking these questions, and the responsibility to preserve that capacity falls entirely on us. If we are not alone, then somewhere out there, someone else is asking the same questions, and the fact that we have not found each other yet means either that the distances are too great, or that the filters are too strong, or that we are looking in the wrong places with the wrong tools at the wrong times. The silence is not permanent. It is just the current state of the data. But the longer the silence lasts, the heavier it weighs, and the harder it becomes to ignore the possibility that the Great Filter is real, that it is ahead of us, and that the reason the galaxy is quiet is because no one makes it past where we are now. That is not a comforting thought. It is not meant to be. It is meant to be a warning. And whether we heed it or not will determine whether future astronomers, human or otherwise, ever solve the Fermi paradox, or whether they become another silent data point in a galaxy full of species who asked the same question and never lived long enough to hear the answer. The galaxy is silent. The universe keeps secrets, and somewhere in the gap between what we can detect and what we can explain sits a question that has haunted every civilization that ever looked up at the night sky and wondered what else was out there. We spent the last chapter asking whether we are alone and whether the silence means we are safe or doomed. But before we could ask those questions, before we could frame the Fermi paradox or calculate the odds of a great filter, we had to stop being afraid of the sky. For most of human history, the cosmos was not a place of wonder, it was a place of terror. The sun rose and set on a schedule nobody understood. The moon changed shape for reasons nobody could explain. And occasionally, without warning, something would appear in the sky that had no business being there. A streak of light, a bright fuzzy object with a tail, a daytime darkness as the sun vanished behind the moon. These were not curiosities to early humans, they were threats, messages, warnings from forces beyond comprehension. The sky was where the gods lived, and when the gods sent signs, you paid attention because ignoring them meant death or disaster or the collapse of everything you knew. Comets were the worst. A comet does not behave like a normal star. It moves, it grows brighter and dimmer over weeks or months. It develops a tail that stretches across the sky, sometimes visible even in daylight, glowing with a light that does not match anything else in the heavens. To a culture without telescopes or an understanding of orbital mechanics, a comet was an omen, a bringer of chaos, a signal that something terrible was about to happen. And the thing about omens is that if you look hard enough, you can always find a disaster to match them. A comet appears in the spring. A king dies in the summer. Obviously, the comet caused it. A comet appears in the fall. A plague breaks out in the winter. The connection is clear. The comet warned us, and we did not listen. That logic, flawed as it is, reinforced itself across centuries. Comets became synonymous with doom because humans are extraordinarily good at pattern matching and extraordinarily bad at distinguishing correlation from causation. Halley's Comet has been recorded as a powerful portent of gloom and doom across history, showing up in the writings of cultures separated by thousands of miles and hundreds of years, all arriving at the same conclusion. Bright object in sky equals bad things coming. The comet appeared in 1066, just before the Norman conquest of England. It appeared in 1456, during the fall of Constantinople. It appeared in 1835 and again in 1910, and both times people panicked because the comet was returning, and history suggested that meant trouble. The fact that Halley's Comet shows up every 76 years like clockwork, following a predictable orbit determined entirely by gravity and having no causal relationship whatsoever with human events, took until 1705 to figure out. Edmund Halley calculated the orbit, predicted the comet's return in 1758, and proved that comets were not messages from the gods. They were rocks and ice following the same laws of motion that governed everything else. It took another century for that knowledge to filter into public consciousness, and even today, if you ask a random person on the street what a comet symbolizes, a distressing number of them will say something about bad luck or cosmic warnings instead of orbital mechanics. Meteors were no better. A streak of light across the sky, visible for a few seconds before vanishing, with no explanation and no pattern. Some cultures saw them as souls ascending to the afterlife. Others saw them as dragons or demons flying through the heavens. A few saw them as pieces of the sky falling to earth, which is closer to the truth, but still wrong in every detail that matters. The idea that meteors were rocks burning up in the atmosphere as they fell toward the planet did not gain traction until the 1800s, and even then, the concept was controversial. Rocks do not fall from the sky. The sky is not made of rocks. Where would the rocks come from? The argument sounds absurd now, but at the time, it was a legitimate scientific debate because nobody had a framework for understanding where meteorites originated, or why they only showed up occasionally, or why they burned so brightly on the way down. The framework came later, after telescopes improved and orbital mechanics became well understood, and someone finally connected the dots between meteors and the debris left behind by comets. Meteors are not omens. They are gravel hitting the atmosphere at tens of kilometers per second. The only reason they look dramatic is because friction heats them to thousands of degrees and the air around them glows. It is physics, not prophecy. But for thousands of years, physics was not an option. Prophecy was all anyone had. Eclipses terrified people. A lunar eclipse, where the Earth's shadow falls across the moon and turns it dark, was unsettling but manageable. The moon was already known to change. A solar eclipse, where the moon passes in front of the sun and the world goes dark in the middle of the day, was existential. The sun is the one constant. It rises, it sets, it does not stop working, except sometimes it does, and when it does, the temperature drops, the animals go silent, and the stars become visible at noon. If you do not know that the moon is blocking the sun and that the event will last only a few minutes, your brain fills in the gap with the worst possible explanation. The sun is dying, the gods are angry, the world is ending. Pack your things, say your goodbyes. This is it. Ancient Chinese astronomers recorded solar eclipses as far back as 2000 BC, and some of the records describe the panic that followed. People banging drums to scare away the dragon eating the sun. Priests performing rituals to bring the light back. Entire cities shutting down until the sun returned and normal order resumed. The fact that the sun always came back did not make the next eclipse less terrifying, because nobody knew when the next one would happen, or how long it would last, or whether this time might be different. The Greeks were the first to figure it out. Anaxagoras, in the 5th century BC, correctly explained that the moon shines by reflecting sunlight, and that a solar eclipse occurs when the moon passes between the Earth and the sun. The explanation was elegant, testable, and accurate. It also got him exiled from Athens for impiety, because explaining eclipses with geometry instead of gods was considered blasphemous. That reaction, the hostility towards scientific explanations that contradicted religious or cultural narratives, would repeat itself for the next 2,000 years. Understanding the cosmos was not just an intellectual exercise, it was a threat to the social order. If the heavens followed predictable laws, then the priests who claimed to interpret the heavens lost their authority. If comets were just ice and rock, then the omens were meaningless. If eclipses were predictable, then the gods were not sending messages. Knowledge dismantled power structures, and power structures fought back. Astronomy likely began in Mesopotamia, though competing claims exist for Egypt and ancient India. The Napta Playa stone circle in southern Egypt, dated to the 5th millennium BC, is one of the earliest known astronomical structures. The Babylonians, around 800 BC, discovered the 18.6-year lunar phase cycle, made the first recorded sighting of Halley's Comet, and created the first planetary movement almanacs. Those almanacs are the oldest scientific documents in existence, and they represent a shift in thinking. The Babylonians were not just recording events, they were looking for patterns. They were predicting the future based on past observations. That is science. Not modern science, not rigorous science, but the beginning of the process. Observe, record, analyze, predict, test. The cycle that would eventually lead to telescopes and orbital mechanics and space missions started with clay tablets covered in cuneiform, tracking the movements of Venus and Jupiter and Mars with enough precision that modern astronomers can use Babylonian records to refine ancient chronologies. The Greeks took it further. Aristarchus of Samos, in the 3rd century BC, proposed heliocentrism. The Earth orbits the Sun, not the other way around. The idea was radical, unsupported by the observational tools of the time, and largely ignored. The geocentric model, with Earth at the center and everything else orbiting around it, fit the data better because the data was limited, and the geocentric model was flexible enough to accommodate epicycles and other adjustments. Ptolemy's Almagest, written in the 2nd century AD, codified the geocentric model and became the dominant framework for the next 1400 years. It was wrong, but it worked. The predictions matched the observations well enough that nobody had a strong reason to question it until better instruments and better math became available. That is how science progresses. Not through sudden revelations or lone geniuses overthrowing the old order, through incremental improvements in tools and techniques that make the flaws in the old models too obvious to ignore. Nicolaus Copernicus published De Revolutionibus Orbium Coelestium in 1543, formalizing the heliocentric model and providing the mathematical framework to support it. The book was controversial, not because it was wrong, but because it was right, and being right meant that the Earth was not the center of the universe. If Earth was not special, then humanity was not special, and if humanity was not special, then the entire theological framework built on the assumption that the universe revolved around us collapsed. The Catholic Church banned the book, scholars debated it, and slowly, over the next century, the evidence piled up until the heliocentric model became impossible to deny. Galileo's Sidereus Nuncius in 1610 used telescope observations to prove that not all objects orbit Earth. Jupiter has moons. Those moons orbit Jupiter. Therefore, the geocentric model is false. The argument was airtight. It also got Galileo tried for heresy and placed under house arrest for the rest of his life because the argument was airtight and the Church had already committed to the opposing view. Truth does not win arguments by being true. It wins by outlasting the people who refuse to accept it. By the 1700s, astronomy was respectable. Edmund Halley calculated cometary return intervals and predicted that the comet observed in 1682 would return in 1758. It did, 16 years after Halley died, and the confirmation turned comets from omens into predictable celestial objects with orbits that could be calculated and futures that could be mapped. The same process played out for eclipses, for planetary motions, for the behavior of the moon. One by one, the mysteries of the sky became problems with solutions. The heavens stopped being the domain of gods and priests and became the domain of mathematicians and physicists. The transition was not smooth, it was resisted. But it was inevitable because the tools kept improving and the data kept accumulating, and eventually the weight of evidence crushed every alternative explanation. The 20th century changed everything. In 1933, Walter Baade and Fritz Zwicky described neutron stars as the remnants of supernova explosions. Subramanian Chandrasekhar calculated the 1.44 solar mass limit for white dwarfs and predicted that anything heavier would collapse into a neutron star or something even denser. Black holes were theorized in 1916 as solutions to Einstein's field equations, dismissed as mathematical curiosities, and finally confirmed observationally in the 1970s when X-ray telescopes detected Cygnus X1, a system where a visible star was orbiting an invisible companion that was far too massive to be anything other than a black hole. Gamma-ray bursts were discovered by accident in the 1960s by military satellites designed to detect nuclear tests, declassified in 1973, and spent the next 2 decades baffling everyone who studied them. The bursts were too bright, too distant, and too energetic to fit any known model. It took until the 1990s to connect them to supernovae and neutron star collisions, and even now, decades later, there are gamma-ray bursts in the data that do not fit the standard explanations. Each discovery expanded the catalogue of ways the universe could kill you. Supernova explosions that outshine entire galaxies, black holes that warp spacetime so severely that nothing, not even light, can escape. Neutron stars with magnetic fields strong enough to disintegrate atoms from thousands of kilometers away. Gamma-ray bursts that release more energy in 10 seconds than the sun will produce in its entire lifetime, and all of it invisible to the naked eye. You cannot see gamma rays. You cannot see black holes directly. You cannot observe a supernova in real time unless you happen to be looking at the right star at the right moment with the right instruments. The threats are there, documented, measured, confirmed, but they exist in wavelengths and distances and timescales that human senses were never designed to detect. We needed technology to make the invisible visible, and once we did, the universe stopped being a benign backdrop and became an active participant in the question of whether life survives. And yet, most of humanity remains unaware, not because the information is hidden, the data is public. The papers are published, the telescopes are scanning, the satellites are monitoring. The problem is that cosmic threats are abstract. A gamma-ray burst from 6,000 light-years away does not register as a threat the way a hurricane or a wildfire or a pandemic does. You can see a hurricane, you can track it, you can evacuate. A gamma-ray burst gives no warning. It arrives at the speed of light. By the time you know it is happening, the ozone layer is already breaking apart and the damage is irreversible. The timescale is wrong for human perception. The distance is too large. The mechanism is too complicated. Explaining why a collapsing star 10,000 light-years away could strip Earth's atmosphere requires walking someone through stellar evolution, nuclear fusion, core collapse, jet formation, gamma-ray propagation, atmospheric chemistry, and ozone depletion. That is a lot of steps. Most people stop listening after step 2. The media does not help. When a comet approaches Earth, the headlines scream about near misses and potential impacts. Not because the comet is actually dangerous, but because fear drives clicks. When an asteroid passes within a few million kilometers, it gets labeled a close call, even though a few million kilometers is more than 10 times the distance to the Moon. The language inflates the threat, and the public absorbs the inflation without the context needed to assess the actual risk. The result is a baseline anxiety about space that is detached from reality. People worry about asteroids that will miss by comfortable margins. They do not worry about gamma-ray bursts or nearby supernovae or magnetar outbursts because those threats are not in the news cycle. They are in the scientific literature, which most people do not read, explained in terms most people do not understand, discussed at conferences most people do not attend. Education could fix this, but education has its own problems. Teaching someone about gamma-ray bursts requires teaching them about light, about redshift, about distance measurements, about stellar evolution, about black hole formation. You cannot skip steps. If you try, the explanation becomes a collection of unsupported claims that sound like science fiction. If you include all the steps, the explanation takes an hour and loses the audience halfway through. The sweet spot, the level of detail that conveys the threat without overwhelming the listener, is narrow and hard to hit. Documentaries try, science communicators try, educators try, and progress is being made. Public awareness of cosmic threats is higher now than it was 50 years ago. But higher does not mean sufficient. A significant fraction of the population still thinks astrology is real, that the positions of planets at the moment of your birth determine your personality and future. If astrology, a framework with no predictive power and no basis in reality, can maintain cultural relevance in the 21st century, then communicating actual astrophysics to a broad audience is an uphill fight. The shift from superstition to science is not a one-time event. It is a process that repeats with every generation. Children are not born understanding orbital mechanics. They learn it, or they do not, depending on the quality of their education and the cultural environment they grow up in. A society that values science produces citizens who understand science. A society that does not produces citizens who fill the gaps with whatever explanation feels right, and what feels right is rarely what is true. Comets feel like omens because they are rare and dramatic. Eclipses feel like divine intervention because they disrupt the natural order. Gamma-ray bursts feel like fiction because they are invisible and distant, and the scale is too large to grasp intuitively. The gut reaction, the immediate emotional response, is almost always wrong when it comes to the cosmos. Training people to override that response, to stop and think and calculate instead of reacting based on fear, is the foundation of scientific literacy. And scientific literacy is the only defense against the next wave of superstition, which is already here, repackaged as conspiracy theories and pseudoscience and alternative facts. The irony is that the more we learn about the universe, the more dangerous it appears. A pre-scientific society looks at the sky and sees gods and omens. A scientifically literate society looks at the sky and sees gamma-ray bursts, rogue black holes, asteroid impacts, solar flares, and a dozen other mechanisms that could end civilization without warning. Knowledge does not make the threats go away, it makes them visible, and once they are visible, the question becomes whether we do anything about them. Asteroid detection programs exist because scientists convinced governments that the threat was real and that doing nothing was not an option. Planetary defense missions like DART exist because someone ran the numbers and concluded that deflecting an asteroid is possible if you catch it early enough. Those programs are not motivated by fear, they are motivated by understanding. We know asteroids have hit Earth before. We know they will hit again. We know the consequences, and because we know, we can prepare. The same logic applies to every other cosmic threat. We cannot stop a gamma-ray burst. We cannot deflect a supernova. We cannot prevent a magnetar from going off, or a black hole from swallowing nearby matter. But we can detect candidates. We can map the sky. We can calculate which stars are likely to go supernova in the near future, and whether their jets, if they form, are aimed at us. We can monitor near-Earth objects and catalogue the ones that pose a risk. We can build early warning systems for solar flares and coronal mass ejections, and create protocols for protecting satellites and power grids when the warnings trigger. None of that happens without awareness. None of it happens without education. And none of it happens if the public treats science as optional or negotiable, or just another opinion competing with astrology and conspiracy theories for attention. Humanity's relationship with the cosmos has evolved from fear to curiosity to understanding, but the evolution is incomplete. We have the tools to detect threats. We have the knowledge to assess risks. We have the technology to respond. What we lack is consensus. Not everyone agrees that cosmic threats are worth worrying about. Not everyone agrees that funding detection programs and planetary defense missions is a good use of resources. Not everyone agrees that science, rather than superstition, should guide how we think about the universe. That disagreement is not new. It has existed for as long as science has existed, but the stakes are higher now because the threats are real and documented and capable of ending everything we have built. The next chapter in this evolution is not about discovering new threats. We have already found most of them. It is about deciding whether we care enough to prepare, whether we build the infrastructure to detect and respond, whether we educate the next generation to understand the risks and take them seriously, whether we treat the cosmos as a place of wonder and danger both at once and act accordingly. The universe does not care whether we figure this out. It will keep producing gamma-ray bursts and asteroid impacts and supernova explosions whether we are paying attention or not. The question is whether we will still be here when the next one happens, looking up at the sky with instruments that can measure the danger and minds that can comprehend it, or whether we will have regressed into old patterns, calling comets omens and eclipses warnings and waiting for the gods to save us from threats we no longer understand. We are the first species on this planet, possibly the first in this galaxy, to understand what the sky actually is and what it can do. That knowledge is not a guarantee of survival, it is a tool, and like any tool, its usefulness depends entirely on whether we choose to use it. The leap from superstition to science took thousands of years. The leap from science to action, from understanding the threats to preparing for them, is happening now. It is incomplete. It is underfunded. It is contested by people who think the money could be better spent elsewhere, or that the risks are exaggerated, or that the universe is fundamentally benign and the threats will never materialize. They are wrong. The threats are real. The risks are documented. And the only reason we have survived this long is because we got lucky. Luck is not a strategy. Preparation is. And preparation starts with awareness, with teaching people that the sky is not a canvas for gods and omens, but a physical place governed by laws we can understand and threats we can anticipate. That shift, from fear to knowledge, is the foundation of everything that comes next. Whether we survive the next gamma-ray burst, or the next asteroid impact, or the next nearby supernova, depends not on luck, but on whether we took the time to prepare while the skies were still calm and the threats were still distant. The universe is full of dangers we have only just begun to catalogue. Some of them are strange, some are inexplicable. Some defy every model we have built and every assumption we have made about how reality works. And those are the ones we turn to now, the cosmic oddities that sit at the edge of understanding, the phenomena that make even seasoned astrophysicists pause and admit they have no idea what is happening or why. Start with nothing, not the absence of matter in the way space is empty between planets. Not the vacuum between stars, where atoms are sparse but present. Nothing in the sense that entire regions of the universe, spanning hundreds of millions of light years, contain almost no galaxies at all. Cosmic voids, vast stretches of space where the matter that should be there, the galaxies and stars and gas clouds that fill most of the universe, simply is not. The voids are real, they have been mapped, they have been measured, and nobody is entirely sure how they got so empty or why they are growing larger. The cosmic web, the large-scale structure of the universe, is not uniform. Matter clumps together into galaxies, galaxies cluster into groups, groups form superclusters, and superclusters are connected by long filaments of gas and dark matter that stretch across hundreds of millions of light years. Between the filaments sit the voids, regions where the density of galaxies drops to nearly zero. A typical void has a diameter of 10 to 100 megaparsecs. 1 megaparsec is about 3.26 million light-years, so the smallest voids span roughly 30 million light-years across. The largest ones, the supervoids, span 300 million light-years or more. That is not a gap between galaxies, that is a gap between galaxy clusters, an entire region of space where the structures that normally fill the universe are missing. The voids are not completely empty. A few galaxies drift through them, isolated and alone, separated by distances so large that light from one galaxy takes tens of millions of years to reach the next. But compared to the dense regions of the cosmic web, where galaxies are packed close enough to interact and collide, the voids are deserts, and they are not small. Roughly 80% of the volume of the universe is voids. 80%. Most of the universe is nothing. The galaxies, the stars, the planets, all of it exists in the remaining 20%, crammed into filaments and clusters that make up a minority of space. The Boots void is one of the famous ones. Discovered in 1981, it sits roughly 700 million light-years from Earth and spans about 330 million light-years across. When astronomers first mapped it, they expected to find thousands of galaxies. They found 60 galaxies in a region large enough to hold 10,000. The void is so empty that if the Milky Way were sitting in the middle of it, the nearest other galaxy would be 100 million light-years away. The night sky would be almost black, no nearby galaxies, no Andromeda, no visible neighbors. Just a handful of faint smudges scattered across a dark sky, and a deep, uncomfortable awareness that you are alone in a way most civilizations never have to contemplate. The KBC void, named after astronomers Keenan, Barger, and Cole, who identified it in 2013, is even stranger because we might be sitting inside it. The local hole, as it is sometimes called, is a region roughly 2 billion light-years across, where the density of galaxies is lower than average. Not as empty as the Boots void, but empty enough to matter. If the Milky Way is near the center of this void, then the local expansion rate of space would be different from the average expansion rate across the rest of the universe. Space expands faster in voids because there is less matter to slow it down. That difference in expansion rate could explain the Hubble tension, the ongoing disagreement between two independent methods of measuring how fast the universe is expanding. One method looks at the early universe and predicts a lower expansion rate. The other looks at the nearby universe and measures a higher rate. If we are sitting in a void, the nearby measurement is biased high because voids expand faster. The discrepancy is not a measurement error, it is a reflection of where we are. The universe is not expanding at the same rate everywhere. It expands faster in the empty regions and slower in the dense ones. And if we happen to live in an empty region, every measurement we make of the local expansion rate is going to be skewed. That explanation has problems. The KBC void would need to be unusually large and unusually empty to produce the Hubble tension, and some researchers think the evidence for its existence is weak. But the fact that it is even being discussed as a candidate solution to one of the biggest problems in cosmology tells you how seriously voids are being taken. They are not minor features. They are structural components of the universe, and their properties affect everything from galaxy formation to the expansion rate to the ultimate fate of space itself. Then there is the Eridanus supervoid, and this one comes with an anomaly that refuses to go away. The cosmic microwave background, the faint glow of radiation left over from 380,000 years after the Big Bang, is remarkably uniform. The temperature varies by only a few parts in 100,000 across the entire sky. Hot spots and cold spots in the CMB correspond to regions of slightly higher and slightly lower density in the early universe, and those density variations are the seeds of galaxy formation. The pattern fits the predictions of the standard cosmological model almost perfectly, almost. There is one region, sitting in the constellation Eridanus, where the CMB is significantly colder than it should be, the cold spot. It spans about 5 degrees across the sky, roughly 10 times the diameter of the full moon, and it is cold enough that the odds of it appearing by random chance in a universe governed by the standard model are about 1 in 50. Not impossible, but uncomfortably unlikely. The cold spot was first noticed in 2004 when the WMAP satellite mapped the CMB in high resolution. Researchers assumed it was a glitch. It was not. Follow-up observations with the Planck satellite confirmed it. The cold spot is real. It is colder than the surrounding CMB by about 70 microkelvins, which does not sound like much until you realize that the entire CMB only varies by about 18 microkelvins in most places. 70 microkelvins is a massive deviation. Something in that region of space is different, and the standard model does not predict it. One explanation is the Eridanus supervoid. In 2015, astronomers mapped the distribution of galaxies along the line of sight toward the cold spot and found a massive void, roughly 1.8 billion light-years across, sitting between us and the CMB in that direction. The void is one of the largest ever detected, and voids have an effect on CMB photons passing through them. As a photon travels through a void, it loses energy. The mechanism is called the Sachs-Wolf effect. The photon climbs out of the gravitational well of the void, and in doing so, it redshifts slightly, losing energy and appearing cooler. If the Eridanus supervoid is large enough and empty enough, it could drain enough energy from CMB photons to create the cold spot. The explanation works, the numbers fit. The problem is that the effect is borderline. The void is just barely large enough to produce the observed temperature drop, and if it were slightly smaller or slightly less empty, the explanation would fall apart. Some researchers think the cold spot is not caused by the void at all. They think it is a relic of quantum fluctuations in the very early universe, a signature of inflation or some other process that operated in the first fractions of a second after the Big Bang. If that is true, the cold spot is not an anomaly. It is a window into physics we do not yet understand, a clue that the early universe was stranger than the models predict. Others think it is just a statistical fluke, a 1 in 50 event that happened to show up in our sky because someone had to get unlucky. The debate is ongoing, and every new CMB survey that confirms the cold spot is still there and still unexplained makes the mystery sharper. Voids themselves are dangerous, but not in the immediate sense. They are not going to swallow the Milky Way. They are not going to strip the atmosphere or flood the surface with radiation. The danger they pose is structural. Voids are expanding. Space inside a void expands faster than space outside it because there is less matter to slow the expansion down. Over time, voids grow larger. They merge with other voids. And as they grow, they tear the cosmic web apart. Galaxies that are currently connected by filaments will eventually be separated as the voids between them expand. Galaxy clusters that are gravitationally bound will survive, but the connections between clusters will break. The universe will fragment into isolated islands, each one a cluster or supercluster, surrounded by a void so large that light from other islands will be redshifted beyond detectability. Trillions of years from now, if dark energy remains constant, every galaxy cluster will be alone. The cosmic web will be gone. The voids will have won. That future is inevitable if the current expansion continues. Voids are the visible manifestation of dark energy at work. Dark energy pushes space apart. Voids, where there is less matter to resist the push, expand faster than dense regions. The process feeds itself. The larger the void grows, the less matter it contains, the faster it expands. Eventually, the voids consume everything, and the universe becomes a collection of isolated island universes drifting apart in an ever-expanding sea of nothing. That is the far future, not the heat death, not the big rip, the fragmentation. The slow dissolution of structure as dark energy tears the cosmic web into pieces and scatters the pieces across distances so vast that no signal can ever cross them. Now take the mystery up a notch. Fast radio bursts, FRBs, brief flashes of radio waves lasting a few milliseconds, bright enough to be detected across billions of light years, appearing at random locations in the sky with no warning and no obvious pattern. The first one was detected in 2001 in archival data from the Parkes Radio Telescope in Australia. It lasted 5 milliseconds, released as much energy as the Sun produces in a day, and came from a direction roughly 3 billion light-years away. Nobody knew what it was, The data was clean, the signal was real, but a single detection is not enough to prove anything. It could have been a glitch. It could have been interference. It could have been a one-time event that would never repeat. Then more showed up. Dozens, hundreds. As of the latest counts, astronomers have detected more than 600 fast radio bursts, and the detection rate is climbing as new radio telescopes come online. Most FRBs appear once and never repeat. A few do repeat, sometimes in patterns that suggest a regular cycle. One repeating FRB, designated FRB 180916, flashes every 157 days, goes quiet for 67 days, and then starts flashing again. The pattern is too regular to be random. Something is causing it to cycle, and nobody knows what. The leading theory is that FRBs come from magnetars, neutron stars with magnetic fields so strong that they warp the space around them. Magnetars occasionally experience starquakes, sudden shifts in the crust that release enormous bursts of energy. If the burst includes a coherent radio pulse, and if the pulse happens to be aimed at Earth, we see an FRB. The theory fits some of the data. A few FRBs have been traced to galaxies known to host magnetars. One FRB, detected in April 2020, came from a magnetar inside the Milky Way, close enough that follow-up observations could confirm the source, but the theory does not fit all the data. Some FRBs are too bright to be explained by magnetars. Some repeat too regularly. Some come from regions of space where magnetars should not exist. The explanation works for a subset of FRBs, but not for all of them, which means either there are multiple types of FRBs with different origins, or the magnetar theory is incomplete. Alternative explanations include colliding neutron stars, evaporating primordial black holes, signals from extraterrestrial civilizations, and a dozen other ideas that range from plausible to speculative to outright absurd. The extraterrestrial hypothesis gets attention because it is dramatic, but there is no evidence for it. FRBs do not carry information. They do not show structure or modulation or any sign of encoding. They are just bright radio pulses, and bright radio pulses are exactly what you would expect from violent astrophysical events. Invoking aliens to explain them is unnecessary and adds complexity where none is needed. But the fact that the idea keeps surfacing tells you how little we actually understand about what is producing these bursts. When scientists do not know the answer, the public fills the gap with speculation, and speculation trends toward the exotic because the exotic is more interesting than magnetars. The repeating FRBs are the most troubling. A one-time burst can be explained by a catastrophic event. A star collapses. A neutron star merges. Something explodes. The burst happens once, and then the source is gone. A repeating burst means the source survives. It pulses, goes quiet, pulses again. That rules out any explanation that destroys the source in the process. Magnetar starquakes can repeat, but the regular cycle seen in some FRBs is harder to explain. Starquakes are chaotic. They do not run on schedules. If the cycle is real, then something is driving it. A binary system where the magnetar orbits a companion and the orbit modulates the emission. A processing jet that sweeps past Earth once per cycle. Some internal mechanism in the magnetar itself that operates on a clock. None of the models are satisfying, and the data keeps getting weirder as more repeating FRBs are found. Then there are the things we have not found but expect to exist based on theory. Cosmic strings. These are hypothetical one-dimensional topological defects left over from the early universe. In the first moments after the Big Bang, as the universe cooled and underwent phase transitions, regions of space with different vacuum states could have formed boundaries. Those boundaries, if they exist, are cosmic strings. One-dimensional objects, infinitesimally thin, but stretching across vast distances, possibly even across the entire observable universe. They would have enormous mass per unit length, enough that a cosmic string passing through the solar system would gravitationally disrupt planetary orbits. They would also produce detectable gravitational wave signatures as they oscillate and interact. We have never detected a cosmic string. Searches using gravitational wave observatories have come up empty. Surveys looking for the lensing effects of cosmic strings, the way they would bend light from background galaxies, have found nothing. That does not mean they do not exist. It means they are either rarer than expected or the detection methods are not sensitive enough yet. Cosmic strings are predicted by some models of the early universe, but not by others. If they exist, they are relics of physics that operated at energy scales we cannot recreate in particle accelerators. If they do not exist, then certain classes of early universe models are wrong, and something else drove the phase transitions. Either answer is interesting, but until we detect one, cosmic strings remain theoretical. Magnetic monopoles are another hypothetical exotic object. In classical electromagnetism, magnetic fields always have two poles, north and south. You cannot isolate a north pole without also having a south pole somewhere. Break a magnet in half, and you get two smaller magnets, each with its own north and south. Monopoles, if they exist, are isolated magnetic poles. A particle with only a north pole or only a south pole. Paul Dirac predicted them in 1931, and they are also predicted by certain grand unified theories in particle physics. If monopoles were produced in the early universe, they should still be around, drifting through space, interacting weakly with matter but strongly with magnetic fields. Nobody has ever found one. Searches have been running for decades. Detectors designed to catch monopoles passing through have recorded nothing. The theoretical density of monopoles predicted by early universe models is low enough that finding one would require monitoring huge volumes of matter for long periods of time. Experiments have tried. The macro detector in Italy ran for years, looking for monopoles passing through the Earth. It found none. The ice cube detector in Antarctica, designed to catch high-energy neutrinos, is also sensitive to monopoles. It has not found any. The absence of monopoles is not proof they do not exist, but it is starting to constrain the models that predict them. If monopoles are real, they are rarer than the simplest theories suggest, and something about the early universe suppressed their production. Then there are the unknown unknowns, the phenomena we have not detected because we do not know to look for them, or because the instruments we have built are not designed to catch them. Every major discovery in astronomy has followed the same pattern. Build a better telescope, point it at the sky, find something unexpected. Gamma-ray bursts were discovered by accident while looking for nuclear tests. Pulsars were discovered by accident while studying quasars. The cosmic microwave background was discovered by accident while testing a radio antenna. Fast radio bursts were discovered in archival data years after the observations were made. The pattern repeats. Discoveries do not happen because someone predicted them and went looking. They happen because someone built an instrument sensitive enough to detect what was already there, and the data forced a reckoning. The James Webb Space Telescope is finding galaxies in the early universe that should not exist. Galaxies too massive, too bright, too mature for the age of the universe when they formed. The observations do not fit the models. Something about the early universe, something about how galaxies form, or how stars ignite, or how matter clumps together, is not captured by the current framework. Webb is forcing cosmologists to revisit assumptions they thought were settled, and the revisions are still ongoing. That is what unknown unknowns look like, not dramatic departures from reality. Small inconsistencies that compound into big problems when you try to reconcile them with the existing models. Inflation, the rapid expansion of space in the first fractions of a second after the Big Bang, is supported by indirect evidence but has never been directly confirmed. The theory predicts certain signatures in the cosmic microwave background, and those signatures have been found. But inflation itself, the mechanism that drove the expansion, remains hypothetical. There are dozens of inflation models, each predicting slightly different outcomes, and the data is not precise enough yet to choose between them. Some models predict relics, leftover objects or fields from the inflationary epoch that should be detectable if we know where to look. Others predict phase transitions that could have left observable imprints on the structure of space. We have not found any of those relics. They might not exist, or they might exist in forms we have not thought to search for. Dark matter is another unknown unknown, in the sense that we know it is there, but we do not know what it is made of. Decades of searching have turned up nothing, no WIMPs, no axions, no sterile neutrinos, no primordial black holes in the mass range that would explain the observations. Every null result narrows the possibilities, but the narrowing is slow, and the parameter space is large. Dark matter could be something we have already thought of, but have not detected yet, because the experiments are not sensitive enough. Or it could be something entirely outside the current framework, a particle or field that interacts with ordinary matter in ways we have not imagined. The longer the search goes on without a detection, the more likely it becomes that the answer is not in the list of candidates we have been testing. Voids are expanding. The cosmic web is fragmenting. Fast radio bursts flash across the sky with no clear origin. Cosmic strings and magnetic monopoles remain theoretical, predicted by models but absent from the data. The cold spot sits in the CMB, colder than it should be, refusing to fit neatly into the standard cosmological framework. The universe is full of phenomena that do not make sense yet, and the list keeps growing. Every new survey finds something unexpected. Every new telescope pushes into a regime where the old models start to fail. And the failures are not catastrophic, they are subtle. A galaxy that is slightly too bright, a void that is slightly too large, a burst that repeats when it should not, a cold spot that is just barely too cold. The universe is not hiding its secrets maliciously. It is just large and old and complex, and the tools we have built to study it are still crude. Radio telescopes can detect fast radio bursts, but cannot always pinpoint their sources. Gravitational wave detectors can hear black holes colliding, but cannot tell you what happened before the collision. Space telescopes can see galaxies forming in the early universe, but cannot resolve the individual stars inside them. The data is improving, the instruments are getting better, but the gap between what we can observe and what we need to observe to answer the big questions is still wide, and every time we close part of the gap, we find new questions waiting on the other side. That is where we are. Sitting in a universe that is 95% invisible, where the structure is dominated by voids that are growing larger, where bursts of radio energy flash across billions of light years for reasons we cannot pin down, where the cosmic microwave background has a cold spot that should not exist, where the theories predict exotic objects that refuse to show up, and where every answer we find raises two more questions. The universe is not malicious, it is indifferent. It does not care whether we understand it. It will keep producing phenomena that challenge our models and defy our expectations, and the only way forward is to keep looking, keep measuring, keep building better instruments and running the numbers until the patterns emerge. The oddities are not just curiosities, they are hints, clues that the framework we have built, the Lambda CDM model that fits most of the data most of the time, is incomplete, not wrong, incomplete. There are pieces missing. Components of reality that we have not accounted for because we have not detected them yet, or because we have detected them but misinterpreted what they are. Voids, FRBs, the cold spot, cosmic strings, magnetic monopoles, all of them sit at the edges of the map, marking the places where our knowledge runs out and speculation begins. And beyond the edges, in the regions we have not mapped yet, are the things we have not even thought to look for. The phenomena that are not predicted by any current theory, that do not fit into any existing category, that will only become visible when someone builds the right instrument and points it at the right patch of sky at the right time. Those are the discoveries that reshape the field. Not the confirmations, not the expected results, the surprises. The observations that make everyone stop and reread the data and realize that something fundamental has shifted. The universe has been surprising us since the moment we started paying attention. It will continue surprising us for as long as we keep looking. The question is not whether there are more mysteries waiting. There are. The question is whether we will be around long enough to find them, whether we will keep building the telescopes and funding the surveys and training the scientists who can interpret the data, or whether we will turn inward, stop asking, and let the universe keep its secrets. The cosmos does not require an audience. It will keep expanding, keep producing voids and bursts and anomalies, whether we are here to witness them or not. But if we are here, if we survive long enough to keep searching, the next chapter in this story is not going to be written by philosophers or priests. It is going to be written by the people who point instruments at the sky and measure what comes back, who find the patterns in the noise, and who are brave enough to admit when the patterns do not make sense and the universe is telling us something we are not ready to hear. 3 times a day, somewhere in the universe, a star collapses and fires a beam of gamma radiation bright enough to outshine 1 trillion suns, and every day, a planet the size of Jupiter drifts through the void, cold and dark and invisible, following a trajectory set millions of years ago. And every second, space expands a little faster, pulling galaxies apart, fragmenting the cosmic web, pushing structure toward isolation. None of it asks your permission. None of it waits for you to be ready. The universe does not care whether you understand it or whether you survive it. It just continues, indifferent, patient, vast beyond comprehension. We have spent the last hour cataloging the ways the cosmos could end us. Gamma-ray bursts stripping the ozone, asteroids punching through the atmosphere, supermassive black holes tearing stars apart, rogue planets wandering into the solar system and scattering everything in their path, hypernovae, magnetars, dark energy, the great filter, and a dozen other mechanisms that sit quietly in the background, waiting. And the thing that should unsettle you most is not that these threats exist. It is that most of them are invisible until they arrive. No warning, no time to prepare. Just a sudden shift in the data, a flash of light traveling at light speed, and by the time you know it is happening, the damage is already done. But here is the other side of that. We know, not perfectly, not completely, but we know enough to map the threats, to calculate the odds, to build the instruments that turn invisible dangers into measurable risks. Humanity went from calling comets omens to predicting their orbits, from fearing eclipses to using them to test general relativity. From cowering under the sky to launching telescopes that can see the moment galaxies formed. That progression, from superstition to science, from fear to understanding, is not guaranteed. It is a choice, and every generation has to make it again. The universe is not required to be kind. It is not required to give us time. It will keep expanding, keep producing bursts and collisions and anomalies, whether we figure it out or not. The only question is whether we will still be here when the answers finally arrive.